Okay, let's start. So, so this is how we are going to run things. So again, we'll just go in the order in which the slides are collated. For teams of one person, obviously that person will present. For teams of two people, both will present in the order the names are on the slide. First person goes first, second person goes second. And for the 3-person team, it would be the two people who did not present during the checkpoint presentation, and again they should just go in order on the slides. Okay, so we'll just follow that. So okay, clear again. So two people go in the order in which your names are: first person first, second person second.
We just practiced our presentation and split up the slides.
Yeah, you can just go in. Try it out. It's useful.
Can we change the order of
No, remember it was going to be random, right? So it is. Okay, so again, first person goes first on the list. You should be comfortable with the whole project. That's kind of the idea, right? I mean, the whole purpose of a team project gets defeated if you're super optimized on one half or the other.
Can we time ourselves? Like make.
Okay, yeah. Can you what?
Can we time ourselves?
Oh, sure, you can time ourselves, but roughly half. Okay, roughly half. Okay. Yeah, you can time yourself, but again, don't defeat the intent. I mean, right? I mean, so roughly half. Okay, and for the 3-person team, it's kind of an honor system. I don't remember in all the cases who was the person who presented. I think in some cases I do, but I do have the recording of the previous one, so don't attempt to bypass that. Okay, so. The other thing is you should stay here for the whole 3-hour slot, so don't walk out after your presentation. And the final thing is, remember, after each project, each presentation, we have some time budgeted for Q&A. That includes not only me asking the questions, but also you guys. Okay, and so engage in that. We have some slack in the schedule because 3 students. So 2 teams effectively dropped out, so we have 12 teams instead of 14. So I think that frees up 20 minutes or 25 minutes or so. If we get done early, it's fine, but we have some slack. Okay, so.
Just to be clear, you don't want to switching off, it's just half-half.
It's not like precisely half-half somewhere.
All right.
I'll let you know.
Sure.
Okay, so I'll just start there and just go to post-processing. Put a timer up here. That sounds good. So should I start and just go to post-processing?
Yeah.
Okay.
Good to go?
Yeah.
Cool. All right. Hey guys, my name is Aiden Cookson, and this is my partner, Matt Nicholas, and our project is real-time activity classification using wearables. So the goal of our project was to utilize the eSense in-ear wearable and a smart wristband to classify and detect a set of similar activities. And our deliverable is a trained high-performing activity classifier, and we also did several analyses of model parameters and feature contribution and sensor contribution. The activities we selected were eating, drinking, smoking, head scratching, walking, and other. The first 4 of these are extremely similar, and that's part of the reason that we selected them, because in a lot of the prior research that we looked at, people were just using a wristband, and those activities would be almost impossible to differentiate without the earable added to it as well. This is our system diagram of our technical approach. The red sections is hardware, and these were our 3 wearable sensors. The left eSense earable, which has the IMU in it, and the right, which has the microphone, and then our MotionSense HRV wristband, which also has a 6-axis IMU in it. So we collected all of the data from these sensors and then split them up into different overlapping time windows. And from this, we used MEL frequency spectrum coefficients for the audio and different time and frequency domain features for the IMU data, which we'll go over later. However, we should note that currently we're not using the audio because the MFCC actually decreased the accuracy, so we're looking into that issue right now, and we hope to finish that before the paper is over. So once we extract our features, these are put into our convolutional neural network, which is implemented with Keras, which outputs a classification prediction for each time window. And then we implement a smoothing function to get our final activity classification. So due to the nature of our hardware, each sensor is connected to a separate device. The left eSense is connected to one phone, and the right is connected to our laptop. And the motion sense wristband is connected to yet another phone, which uses its proprietary M-Cerebrum application. This application proved to be extremely useful also in generating our truth values because it allows the user to manually press a button, like a start and end button, and we can save different time labels or different labels with timestamps, so we always know what activity is going on. The main issue, which we outlined in our midterm presentation with this, is that with having these three separate devices and the data coming in from three separate devices, all at different times, the timing is not synchronized. So to overcome this issue, while wearing the wristband, we took the left eSense, which has the IMU in it, and held it in our hand and did like a punch or a clap. And this created an impulse in the audio and both accelerometers, which we were able to align to help synchronize the data. So after splitting the data into different overlapping time windows, it is possible to just use the raw IMU samples. However, our sampling rate was so highly variable, in some cases from 20 to 100 hertz, that this was impractical to just use the raw samples because the input has to have the same length. So instead we decided to just calculate features on each window. This is a list of our features that we are using currently. We have both time and frequency domain features. To select the time domain features that we wanted to use, we looked at different prior relevant work, and these seems to be the most commonly used and the most effective. And then for the frequency domain, as I said earlier, we're using MFC coefficients for the audio, and we are doing the fast Fourier transform of the IMU data and then binning by taking the mean at different frequency ranges. And this is our network architecture. It's based off of the CNN that Vikrant went over in his lecture. So since the time windows are much shorter than a typical activity might be many seconds, while our time windows are only like between 1 and 5 seconds. And they're overlapping, the prediction data can benefit from a smoothing step to remove any erroneous predictions. We looked at several methods, including a low-pass filter in the frequency domain and a sliding window function, or a convolution of a window function in the time domain. And we also looked at just filtering by the minimum activity length, which is what we're doing here on a portion of our test data. So you can see the top graph. This projector is kind of low resolution, so it's hard to read, but the top graph is our truth data, and the middle graph is our raw prediction. And then the final graph is our smooth data. So basically we just removed all of these really small impulses because it's not likely that the user was like walking and then eating for half a second and then walking again.
Yeah, okay, so these are some of the various metrics that we used to analyze our classifier. First, we just have a confusion matrix, which is a table that visualizes performance. Here's the output of our network with a window and stride length. Basically, you can see that other was one of the more difficult to classify because it basically encompassed every activity that wasn't our activity that we were classifying for. We used classification accuracy, which is pretty straightforward. It's just the number of correctly classified instances divided by the total number of instances. But you don't want to just use classification accuracy because if you have an imbalanced data set, it can sort of give misleading results. So we also use the mean F1 measure, which is the harmonic mean between precision and recall. Precision being the true positive divided by true positives plus false positives, and recall true positives divided by true positives plus false negatives. You get a F1 measure for each activity, and then you average it to get the mean F1 measure. So here's some of the results we have with different window lengths and stride lengths. You can see that it performed pretty high in most cases, especially we decided that the 5-second window length with a stride of 100 milliseconds gave our optimal results, where we had a classification accuracy and F1 measure of around 98%. We also ran this model on the 5-second, 100 millisecond stride length with different number of epochs when training. And we decided that 40 was the best trade-off between the time it took to compile and train the model versus the accuracy. And we were worried when we were getting down to 1680 that we would be overtraining. So we went with 40 as our best. This is something that we're going to finish up in the next couple days. We're basically going to do holdout testing on some of the various features. So we'll pre-process the data without the mean feature, run the model, and see the difference in the output without mean and with mean. And from that, we can determine basically how important each feature is. If the feature only drops the classification accuracy within like 1% or so, we would say, okay, it's not very important. And we would just remove it from the model because then the model would be able to train far quicker. The same goes for sensor contribution, and we don't expect to take any of the sensors out, but we do think that it would, by holding out certain axes of different sensors, we can really see which is the most important for classification. So we did achieve a very high accuracy in classifying these very similar activities, but it's important to recognize the weakness of these models. First of all, it was a very highly controlled environment that we were taking data in. We were only performing one activity at a time. If this were to be generalized to the real world, people can be doing multiple activities at once. They can be walking and eating at the same time. That's something that our model would not be able to account for right now. In order to account for that, it would actually need to be trained. That would be a separate activity in itself, is the combination of activities. So the classifier would have to basically be trained for every combination, as well as any new activity that you would want to include in the model. You could also see that we had a bit of a lower classification accuracy in F1 measure, specifically for the other. That's because it basically is everything that's not the activities we were classifying for. If we were to do this again, instead of training it on other activities, we would only train it on our activities, and we would essentially look at the confidence of the prediction, and if it's below a certain amount confidence, we would then classify it as other rather than directly training it on an other activity. We also only trained on us two, and it's possible that other people eat differently and walk differently, and so it's not necessarily robust for that right now. So for going forwards, it's always better to have more data, and so we may collect some more data in the next few days. As Aiden said, right now the MFCC isn't actually contributing, that's the audio data, to our classification accuracy, and so we're going to investigate that in the next day or so and determine why that might be the case, whether it's bad data or if it just doesn't have as much predictive power as we may have hypothesized before. We're going to perform the holdout feature testing, and if this were to continue past the due date, we think it would be useful to be able to build an app that can communicate at once with every device, because then we can just port the model to that app to perform real-time classification. So, yeah.
Great. So a few questions from my side. Did you manually just hear the acoustics, the audio that you have recorded, and can you make out something about the activities there?
We can, yeah. We played back the audio, and you can hear, because when we did eating, it should have not been eating, it should have been eating chips, because we knew that the chips make a loud crunch. And we played back the audio, and we could actually hear that. Okay. But when we added the MFCC to our neural network, our classification actually dropped about 5%. And so.
And did you try just with the audio? What was the accuracy? Like if you were to.
We haven't tried.
That's
it
a
with
good
just
test.
The audio, yeah.
We should definitely do that.
Okay.
It is one hypothesis is that that microphone is fairly quiet, and a lot of the activities we're doing are pretty, like, it's very hard to pick up. Like, I have to put full volume on my computer, so it might have a pretty bad signal to noise ratio.
Okay. And also you said something about you don't expect dropping sensors to help at all, right? Or,
yeah.
Right. So why do you think that's the case?
So for eating and drinking, the biggest difference on the wrist, because from the wrist sensor it looks basically the same, right? Is the tilting of the head when you drink, and so that contributes with that. I suppose head scratching, we wouldn't see that much of a difference. Walking, we think there's like a good difference with in there. What's another one of our activities?
Smoking.
Okay.
Yeah, smoking. just different head poses we think had a good difference.
Anyone with questions?
Yeah.
Because sometimes when we processing neural network will consuming long time. Right? So sometimes how do you deal with that problem? Because some neural network, especially deep learning, it will when we process it, it will consume a lot of time. So how to deal with that?
So just to make sure the question is clear. So are you worried about the computation time of the?
Yeah, computation time. Maybe it will.
I think
Like the training time or the computation time in real time?
Computation time.
In real time.
The detection time, right?
Real time.
Oh, okay.
You're doing it offline.
I
right?
think-
mean,
Yeah,
Yeah,
doing it
currently we're
offline.
doing it offline. I think if we transition to a real time application, we should have plenty of time because our windows are between 1 and 5 seconds right now, and then our stride length is at least 100 milliseconds. So as long as it can
Yeah, that's
perform at
fast.
100
Yeah,
milliseconds,
that's
but
fast.
yeah.
So the punch thing, are you doing it after every, like, was it done just once, or have you done multiple of those and done something? Because, like, you can't have the same calibration throughout the experiment, right?
Yeah, that's a good question. We do it every single time we took a new run of data.
know.
So we would start recording, we'd punch, we'd save that data in a folder, and then when we ran pre-processing on that data, it would then sync up all the time to one of the
So
devices.
it's every several minutes, every couple minutes.
So when I have to use your application, maybe, so I have to do first the punch to calibrate it.
So we don't really have like an application right
Yeah.
now. This is running offline. And if we were to build a real-time application, it would be using one device connected to all
Mhm.
three, and so we wouldn't have that issue.
Yeah.
You mentioned that you extracted F50 as a feature, right? But the sampling rate is variable. So how did you account for that?
How do we cover this? So we just assumed that it was like pretty low because it ended up the average like over all of our data was like 20 hertz. So we just used 20 hertz for that. But you're right that it would be slightly off. Yeah.
How are you able to collect so much data? Because the confusion matrix had like over like 10,000 values in there.
Because of the stride length. Basically, we make a classification for every 100 milliseconds or 250 milliseconds, depending on the stride length, or half second. I forget exactly what they were. So 1 second of data would turn into 10 instances.
So you just do like the same activity over and over in like 10 minutes?
When we were taking training data and test data, we would perform usually 2 or 3 activities at a time and mix them up. And then for our test data, we would do 10 to 15 or 20 minutes straight of just alternating random activities.
Okay, I think let's move on.
Good.
Thanks. Can you move to the next slide?
Thank you.
Yeah.
Yes.
Okay. So I guess it's going to be Julian and Ria, right? Yeah.
What? Let me just put the chronometer. All right. Hello, everybody. I will present our project that was directed me, Indoor Navigation System for Visually Impaired People. It was made by my teammates Rija Amirali and me, Julian. So basically, our goal was to make a voice command system to help blind people navigate in a specific room, in an indoor location. For this, we had some specific aims. For example, for it to work with ultra-wideband real-time ultra-wideband location system, for it to have the calculation of the shortest path to the desired destination, for there to be an Android app that recognizes the speech of the user, and also could have speech synthesis to say the commands to the user. Usage of Bluetooth beacons to improve the error rate of the UWB system, and integration of the different subsystems that it comprises.
Okay. So we went through, we showed this slide the last time, but one thing that we have added during this time in between is we made a wearable device that consists of the UWB tag. The tag is the one that stays with the user and gives the user's location, and that is BNO055, which is the 6-degree freedom IMU sensor consisting of accelerometer, gyroscope, and magnetometer for the orientation. So that stays with the user, and I'll give a brief overview of this system, which we will cover in detail in the subsequent slides. The Uwb anchors help determine the location of the user with the tag. These are the anchors. It communicates with a server through a broker, because we're using MQTT protocol, which needs a broker, and Raspberry Pi is being used as a broker. And there's the Android application, which the user interacts with the Android application to specify the destination, which is then sent to the server. The distance is calculated and it guides the user, and the Bluetooth beacon is for the last 20 centimeter offset that is there.
So this is basically a map of the room where we test this project. The stars represent the UWB anchors. Here are 8 anchors, but at the end we use 6 because like the accuracy of the UWB system depends very much on how you place them. And we discovered that, and testing with different UWB placements, we discovered that with 6 it was the most stable configuration. Yeah.
So you mean actually putting more was hurting your accuracy?
Yeah, like with 8 it was very unstable, and then we shut down 2, and yeah, it got better.
6 was what we thought was optimum number.
Yeah.
So this is the app server process overflow. What happens is the Android application actually asks the user about the destination, and we use some destination like microwave, monitor, the ones that we were testing with. So that destination is sent as a JSON object to a server, the CGI server, and the tag along with the IMU sensor gives the XYZ coordinates as well as the angles. So the microwave or the monitor, whatever is spoken, is the destination. The tag becomes the source. So essentially, that server is calculating the distance between the source and the destination through A-star algorithm, and then the instructions are sent back to the application, which help guide the user.
And well, you can also add new locations. Like there are some hard-coded destinations, but the user can also add its own location. And then we have the shortest path algorithm that is basically an A-star that uses a visibility graph. So a visibility graph only consists of a normal graph where the links that join the nodes are like made in the like only when those nodes are visible. Like for example, in our room we have a conference table at the middle of the room, which was our main obstacle. So we determined 4 nodes that corresponded to the 4 corners of the table, and we had 2 arbitrary nodes that were the start and the goal position. So depending on where the user wanted to go and where the user was at that moment, it calculated with which nodes it could make like an edge, a link, based on if it was visible with that node. And it was the same with the goal. So for example here, the start is only visible, well, it only has a visible connection with 1 and 0, but not with 3, goal, and 2.
This is the interface of the application that was created. It starts with the specify destination or command. These are some of the responses. The main one is the destination, which is specified. After communicating with the server, it starts guiding like walk for X meters or rotate by Y degrees clockwise or anti-clockwise, depending on where the user has to go. And there are some other features also, like add, the one that he was talking about, where we hard-coded some of the specified destination like microwave or monitor, but the user could also add some new destinations depending on their preference. There's also a pause button. You could always, and to resume, you could double tap the screen. If you want to go from just specifying the destination to a command, you just tap twice. You have add, you have pause, you have return to just return back to the instructions, and then you just have cancel, which simply just goes back. That's the interface over there. And this is. You want to go?
Okay. So, and basically, how you add an object is like you are the blind person is like following the navigation the route to its destination, and if he finds something he wants to like he has a bottle and he lives in a table, he can pause the app and say he wants to add the location. So when he arrives to the other destination and wants to come back to the bottle, he only specifies guide me to the bottle, and it guides to the bottle. No? And when the user arrives to the desired destination, the app says, well, you are already arrived to your destination, and because there's an error rate in the UWB system of more or less like 20 centimeters, the Bluetooth beacon sensing is used in order to breach this offset. No? And how it works is that, well, we have this tiny Bluetooth beacon that sends a signal. So the smartphone vibrates proportionally to, well, its vibration intensity is proportional to the received signal. No?
So the experimental evaluation just deals with some of the findings that we had, and as it was mentioned before, after using 6 anchors in the system, there was an error of 20 to 30 centimeter, mostly it was 20 centimeter, and it was much more, but we were able to improve it a little bit by changing the positions, but it came down to 20 centimeter. And then there was a pose estimation factor which was calculated according to the user's body, because we placed that system in along with the wearable in the hand, was placed in the pocket also, and from the center of mass of the body, it was just calculated for one person around 20 centimeter. So we adjusted that, and we tested the system only on 3 participants, the 3 of us, and we found that after placing this. Placing the arm on the side with the IMU sensor pointing downwards, it was the most accurate, and Bluetooth beacon was able to help breach that offset of 20 centimeter, except with a microwave, because we read somewhere that the microwave and the Bluetooth, the beacon uses Bluetooth, they operate on somewhat the same frequency. So there was a little error with that. Otherwise, it was fine totally.
So, well, we have some examples of our work. Well, I think it would be better if we continue with for the strengths. What are the differences between this and other prior work? I think the most the best one is that this provides a calculation of a path, of a shortest path from a user location to a destination. Obviously, it's more or less you need to hard code a room, you could say that. And also that to compensate for the fact that the UWB system isn't that accurate, we use a Bluetooth beacon. Also we have some interesting features adding new locations. And that thing about taking into account the user's body in the calculation of the location.
So the biggest limitation that we observed in the project was that there was a need for Wi-Fi connection for the whole UWB system, and if it wasn't present, then the system did not work. And one thing that we feel can be an improvement is obstacle avoidance, because the conference table that was there in the setup where we were testing the system was the biggest obstacle. So that could an obstacle avoider path could be added in the search algorithm, and we could try with changing the configuration of the UWB anchors a little bit. And we also came across this thing, WeWalk, which is one of the best 20 projects of 2019 for blind people. So what we could do is you could integrate the users, the wearable system with the cane, and which would help, which the blind person could use in order to navigate the room.
Well, there's a demo, but I think the time doesn't. And basically, this is what each member did. No, Amir worked with the MQTT. I work principally with the server, and Rija with the Android application, and that's.
Well, that was okay.
Great. So, when you're talking about the shortest path, it's not like the direct path, it's around the furniture.
Yeah.
Right?
Mhm.
Okay, just want to make sure. And
Uh,
how much
oh.
did the presence of Bluetooth help in terms of accuracy?
Well, like the UWB system, like this is a bottle. It guides you like until here, and like you have all these like it helps now. Like if you have the hand in here, it more or less helps you to see where to put the hand. But yeah, it's a very small like range, no? But it's useful. I think in the demo it's more or less shown better, no?
Wherever we felt that the vibration intensity was the highest, we could see that the place, the thing that we wanted to reach was there. So it was helping with the final little distance. I was
Yeah, like you play the
Yeah, you can maybe play one.
Ah, yeah?
just like the part of the adding the new
Okay.
features and going back.
That was probably 232.
Okay. Well, I don't know.
Okay.
No.
I think I also.
Oh, sorry. Sorry, this is So's account.
Yeah,
Okay.
Well,
Go back to the presentation.
I don't know how to.
No, we need to request access.
No, there is a link on top of it that opens.
Oh.
Yeah, but. Sorry.
Okay, too many
Yeah.
icons. So you should go to the one for preview. You should step to the right.
To the right.
Right
Hi. Do you know how
Okay,
to?
just
Yeah. Sorry.
just do clover edge so that the browser closes.
Here, I think.
This red one.
No.
This
Yeah.
one. Yeah.
Okay.
Okay.
No, don't kill any windows.
Oh, okay.
They're all precious tabs.
Yeah. Sorry.
Okay.
Yeah.
There you go. So you.
Yeah. It's
there's a
the link. Yeah, to YouTube. Yeah, I think it's better. Yeah, we want to only post the relevant scenes because
32, right?
I don't know. Well, that's like
Please specify a destination or command. Rotate 104 degrees anti-clockwise. Rotate 41 degrees anti-clockwise. Or for 1.2 meters.
You need to make all the movements slowly because
For 0.5 meters. You already arrived to your destination.
reliable with like fast movement.
Specify a destination or command.
Well, we added a bottle of water.
Rotate 112 degrees
Here it will
clockwise.
guide us to that
Rotate for 66
location
degrees
that
clockwise. Walk for 1.6 meters. Walk for 1.4 meters. Walk for 0.7 meters. Rotate for 73 degrees clockwise. Walk for 0.8 meters. You already arrived to your destination.
Yeah, I think that most.
And then like after that, it shows the Bluetooth is turned, like the Bluetooth button.
Yeah, this.
Okay. Any questions?
Wait, I think there's.
Okay, there are many.
So I noticed that your app is like saying them to move like a precise degree and a precise distance.
Yeah.
But if you like consider that in the real case, how does the blind people understand the motion of angle and the motion of distance?
Oh,
Yeah.
So that
maybe
is.
we could like use something else, like maybe
Yeah, that
walk some steps or something like that.
that is one thing that we noticed because we were using angles like rotate 150 clockwise, anti-clockwise, but we realized that not everyone might be having that mathematical bent of mind of turning 150 degrees. So probably one thing that we could incorporate is keep turning until that person has actually turned according to that angle, and then we could start asking them to move. So that is one thing that we can incorporate.
Yeah, in fact, we put it in like the limitation.
Yeah, that.
And like you mentioned that like when the user comes within 20 centimeters of the object and the button starts to like or something, we have like a quantitative results like actual error. I mean maybe some sort of
Of the error of the estimation of the distance between. Well, like for here, it doesn't matter that much because we don't want to make give a sense to the person of where it is. Like we want to give the person a sense that the object is not here on here, but it's like in this area. And like here, you can like if you only move like your hand a little, you'll find like eventually the object, no? But it's like more or less to give you the sense, no?
Does an error of pose estimation, state estimation of a person accumulates over time, or it is just bounded by some value?
Error
I mean, coordinate of the person.
Oh, you're saying are there any errors with that?
Yeah. I mean,
No. So one thing that we did notice is that when we were turning too fast, then there was a little error with the angle. But when we turned very slowly, there wasn't a lot of error. It was more or less accurate. There wasn't much error.
But what you're saying is that if it's like a stateful application, like it saves the location of the user.
Yeah, kind of. So it doesn't save it, and
No. What it does is like every time the app communicates with the server calculates the path in that instant. Like there's no state saved.
Okay.
Yeah, it's all real-time computation.
So do you get 2D or 3D locations?
We only have a 2D XY because the Z-axis is like with UWB systems it isn't like that accurate. Like we investigated some a little, and we saw that that depends more on the way you place the sensors, and even if you place them like in the best way, like there's a greater margin of error than in the XY. So we didn't really use the Z-axis, but it would be like a good improvement.
So the height of like the sensor on the person might affect the distance they are from all the UWB.
Yeah, but then
No. Like the person is just taken into account as a point in the XY plane of the room. So
that user has
the system calculates XYZ. It's just that Z is working at.
yeah.
user has a tag. It's basically the coordinates of the tag which are being used as a source.
Guys, we need to move on.
If we add numbers, how would that be? Maybe the accuracy can be improved.
Added number?
Add more anchors.
More without.
We tried with 8, but it was generating more instability than with 6. So it depends on the number of anchors, but also in its placement and I like placement. I like it's very complex.
I'm surprised that it's reducing accuracy. But anyway, thanks.
Oh.
No.
Yeah.
Okay. So we just press an arrow, right?
Alright, so today we'll present our project, which is the audio and video synchronization. So basically what our project is going to do is we're trying to solve the issue on the lags that it encounters in streaming services. So our goal is to create a system that allows for end users to do audio video visual synchronization on their end devices. And the key aim to working on is that we understand the situation that when there's an audio leads of 45 milliseconds or a lag of 125 milliseconds, that the end user can definitely recognize that. So that is our main criteria for the success of the system. And for simplicity, we're trying to working on a single person front of pose case because that kind of relieve all the issue for us to get the right features we need. And for the adjustment we're doing on the audio, because that's more simple for us to introduce the delay we want to have and our adjust video files for the users. And our deliverable will be simply a defined stack or a system that's able to do all these tasks in a very smooth fashion. So capture the videos from the streams and identify the offset and be able to inject the proper time offset into that address file and let the user play it out. And we will also have our training data sets, validation data sets, and the codes we implement for all these features as a whole. And then we will also have a complete demonstration that's going on in the following stuff. We investigate a lot of prior works in terms of the audio-visual synchronizations, and the most promising one we found is the syntax. So basically, this system they created, they took like 5 frames of from the video stream as well as 5 frames from the audio streams, and they took each of them fit into the neural networks separately. So from each neural networks they will output a factor that contains the feature of the respective streams. And then what they do is doing cross-correlation between these 2 factors to tell that whether the audio and the video streams are synced or not. So based on their inspirations, we decided that we want to find our own features to use in our own correlations for our presented system. So we're looking on some mouth tracking one, and we looking at some lip reading, so basically track the lip motions, and also the mouth aspect ratio, which tells you that whether your mouth is open or not. And the voice detection, we particularly want to work on like voice activity detection. So for this one, basically will allow us to tell that whether a segment of the audio will have the human voice presented or not. And we're also looking at the male frequency, but that will be more complicated as well. So for video capturing, we simply create a Python script that uses FFmpeg impact to let the user grab whatever they want from their screen. So basically, it will pop up the screenshot of your screen, and then you select whatever regions you want to record it, and then we just let the FFmpeg record the streams on its own, and the user can decide when they want to stop the recordings. And basically, our systems were using this and capture the entire strings the user really want to that is synchronized by our system. For the methods we have, like from the midterm presentation, we have 3 strategies for sure. So the first one, in the recap, is a direct approach at doing neural networks on both string and using a brute force way to get out the offsets. And the strategy 2 is what I described earlier, that we get our own features from the mouth and the voice and do cross correlation. And the third one is inspired by the syntax, so we're trying to do a variation based on what the syntax inspires, like due to neural network training, and identify the genuine and false pair between the audio and the video pair alignments, and see whether we will be able to optimize the distance between those 2 to see the things is synchronized.
I'll just go to to the very. Okay, so we went through like essentially how we went about going through different strategies, but we selected strategy 2. Essentially, what we're doing is we're splitting audio and video. Specifically for video, we're looking at mouth aspect ratio. We're essentially extracting these features from the video stream, determining essentially how big the mouth is. And from the audio side, we're using voice activity detection, determining which portions of the audio correlate to sound and which portions don't, and assigning a binary value to that. In terms of data sets, so we have online videos, which include full frontal pose of like a person speaking, as well as our own recordings. And what we actually do to test our processing is to actually manually inject these delays and essentially try to recorrect them. So in terms of synchronization steps, first we separate the audio and video with FFmpeg. We essentially, from our training set, we've optimized for this VAD parameter that determines just how aggressive you want to be in terms of determining whether a section of audio is voice or not. So we've used the training set to optimize and find the best parameter. Grab that from Google Drive. This is where the novelty of it is we've actually used, so we use VAD for audio extraction, and then open mouth detection for video extraction. And then from these features, we essentially run a cross correlation to find essentially the best time offset, determine what that offset is, of course, and then re-inject them into essentially and make it pretty much a new file. So we have this
demo.
Okay, so first we're gonna.
Out loud. George Bush doesn't care about black people.
Okay, wait. Is this the sound? The audio? It's not. It's coming out of here, not the.
Yeah.
It was just popping out.
No, Unfortunately, it's going to be on that side. I don't
Okay.
Yeah. Maybe you can just turn it louder.
Louder. Okay.
Yeah. So essentially, we're playing right now the delayed video, which has like significant issues. We got this from the SyncNet paper. This is what they used for their processing.
Well, today, Kanye West has a lot of people wondering if he cares about black people.
Yeah.
Remember Kanye West
So
tweeting
essentially,
today, you don't
We have a huge offset of 1 second in this video. Okay, so now we close it, and now we're going to actually run it. We're going to essentially start the delayed video again, process it while it's playing,
said out loud,
and then reinject it.
George Bush doesn't care about black people.
And then we have we essentially
today,
replay the synchronized
Kanye West has a
video
lot of
from
people
where we
wondering if he cares
stopped it
about
earlier.
black
So
people.
this is the fixed
Kanye West tweeting today, you
sync
don't
audio and
have-
video.
Yeah.
Okay. Shoot. How do I go to? Sorry.
Sorry.
I have too many tabs.
Yeah. Okay. All right. So just gonna go through the results. So this is just an example of what we're actually doing. We have the video and audio features there, and we're running a cross correlation to find the best optimal offset, essentially.
Yeah.
So these are some kind of originally for mouth aspect ratio, we had it as a binary value as like open or close, essentially. But we found that we were losing a lot of information from that. As we can see, we were getting like a pretty significant amount of error with that. So by not turning into a binary value using raw mouth aspect ratio, we get much better results. And as we can see, we can actually get pretty consistently negative, like -1 or -2 frames error in our, essentially in our determination. Now, the reason for this is because when you actually open your mouth to start speaking, you open your mouth before the voice actually comes. So that's would actually explain why we're seeing like a pretty consistent offset between the two. Now we can actually, in our future work, we can actually take this into account and actually optimize it and make sure that the offset is even better than that. But already we're falling within the range that we're looking for. So some of the key findings. So yeah, mouth aspect ratio and voice activity detection have a really good correlation. Using raw mouth aspect ratio is better than using a threshold. And also, there is a lag between when a person opens their mouth and then actually starts speaking. In terms of metrics of success, we've met fast processing, small error, and also the smoothness of the synchronization in the played video. In terms of strength of weaknesses, the processing time is pretty fast, relatively speaking. Again, it depends on how fast your machine is, of course. And ideally, this does work for any offset in audio and video, no matter how large or small it is. And also, this is a pretty relatively simple essentially decision-making system. It's not a convolutional. There's no CNNs involved. You know, if you get like garbage data, you actually know why you're getting bad data. So it's much easier for like an end user to interpret and to understand. For weaknesses, it is restricted to a single person like frontal pose videos, and we can't right now take into account transitions between when, you know, let's say the speaker disappears from the scene, we lose track of their mouth, and then our data can become a little fishy. Once we actually implement like kind of a frame window implementation rather than using the whole video, we can, you know, cut out like times when, you know, for example, there's more than 60% of the window is, you know, there's no mouth detected, for example. So we can take that into account. And also we assume that the speaker makes pauses in his or her speech. Again, we're relying on those kind of like the open and close of the mouth. If they're continuously speaking quickly, then we're not going to be able to find many distinct features from that video.
And for our future directions, since we only work on a single person, so we do expect that for the future development, we should make it even working on multiple speakers in the same video streams. And we also want to working on the movement correlations with the phonings that is spoken out by the speakers. And also to reference to the limitation of like the speakers are temporarily disappear from the scenes, we also wish that if there were more features we can use in order to take account these special cases that we cannot lose one of the features we use, but we still have the other to compensate for the correlations we want to do. And then the last one we really want to do is try to resolve that visual cue before the voice actually comes out from your mouth. So that will be the last things we'll do. And the remaining step for our project is to implement the smaller window size for our correlation, because since we, from the first development until now, we're still working on the entire full video files. So we want to minimize that maybe we can just work on a portion of it. And then we will do cleanups and wrap up all the things we created, including data sets, code and script, and do documentation for all of them.
Yeah, and then this
And
is
it's our individual contributions.
Yeah.
Great. Thanks. Yeah, I don't have any particular questions. Anyone else?
Yeah.
Does it work when there's like the speaker is speaking and there's like a zoom in and zoom out, like it said that like the speaker, like it doesn't identify when the speaker isn't in a frontal position?
Yes.
But does it work when like there's this camera and it is zooming to the person?
Well, we haven't tested with that specifically, but as long as the mouth is recognizable, then there's no reason why that shouldn't work.
Yeah.
The issue is that once you start going to the side, then the mouth is harder to like actually extract and actually determine what the aspect ratio is.
You outlined like 3 approaches, one of which was just like using a CNN. How
Yeah.
would you generate truth values for when the audio actually should start? Would that be a manual process, or is it just assuming when the mouth opens?
Wait, so for our first
strategy?
Yeah, I mean, like our first strategy was pretty much just like we're taking like frames of which we had like a window size, and we were looking at like the spectrogram of like the audio and just feeding that straight into a CNN and hoping to get some sort of like output, but we were just seeing a bunch of overfitting. It was a very brute force approach,
and which means that's not really efficient for us to find the offsets. Because it would do a lot of some irrelevant stuff we don't really need.
Yeah, that was something we explored at the beginning, but we quickly moved away from that to like more elegant approaches. So our second and third strategies were better, but we ended up going with the second.
So in this, is it possible that there's some background noise as well and the speaker is speaking? So there's like 2 components of audio simultaneously and still it syncs?
So we've been testing with videos where we just have the single speaker like present and speaking. The purpose of the voice activity detection, although we haven't tested this with instances where there's a speaker and there's like background noise, the purpose of that is to actually separate that essentially. So the actual implementation of the VAD is, I'm not as familiar with that. But ideally, it would like be able to separate noise from what the speaker that's actually speaking, and actually determine what's voice and what's actually not.
And it just takes. So you are assuming the ideal speech case for the system as of now.
Yeah. Well, right now we're only right now we're only working with the ideal speech case. Yes.
Yeah. So that's one.
So for the test cases that you presented, it was a constant offset from audio and video for the entire time.
Yes.
For streaming cases, you can certainly envision, and you've all
there might be some
changes.
Yes.
How would you modify what you have here for potentially variable labs?
So I think one of our strategies is to implement the smaller window, so like we can actually target at the particular portions you want to working on. So like let's say you got the offset change in the middle of the videos, and we will, while future direction we're working on this, like we just target at the parts that after that change, so that our new offsets for the time shifting will simply based on the things that's after the change. But right now we still have the entire things working on, so that will be a limitation for our current systems. So I hope that will be a way to account for the varying like offsets in the streaming videos.
Okay, let's move on.
Okay.
Great, thanks. Can you go to the next slide?
Yeah.
Hi everyone, my name is Jinqi Li. This is Chaohao Li, and our third team member is Gabriel sitting behind. So our project is locating and visualizing wireless signals. So a overall project goals will be develop a AR application to visualize the wireless source. We can use the localization to determine the the location of the source, and given the camera aimed to the source, we can draw a circle around that to keep track of that source, and we can display the information captured from the source, and also we can track the source like while the user is moving around. And the other part is most researchers most research focus on finding the DOA, which is the direction of arrival, using antenna arrays. So we really want to cut down the cost of hardware. So for this project, we use only 2 receiving antennas, and we use local information to locate the source of the in that AR image. So first, a simple introduction would be to locate a wireless signal source. We use phase difference to tell the azimuth and aggregation angle from that wireless source. And then we input that data to a AR platform so we can keep track of that wireless signal source. So some prior works would be the WINE project, which is focused on the wireless signal receiving, and the Wi-Fi receive part. We are basically based on that and made some modification. And for the AR platform tracking, we use the paper on the right, which the AR platform based a lot on that. So the Gen radio is one of the main tools we use here. So we actually want to measure the phase difference, but due to the limitations of our hardware and resource, we turn to measure the time difference and translate that into the phase difference. And then since there are no existing Gen radio module that's available for us to do the time differentiation, we create our own. So to do that, we create a synchronized block which handle the stream input, the input stream 1 and program to detect the peaks of the received waves. So make sure we're not just comparing unnecessary values, but the peaks. And also we calculate the time delay between the peaks and output the time difference. So this is a flowchart we do. It's kind of hard to see, but okay. So here's an ideal situation. We had a pure cosine wave goes to a low pass filter. Well, that's not necessary, but I put in there, and we delay for 100 samples, and we feed them to the block we design and display them. So here's our 2 waves. The blue one is the first wave, and the red one is the second wave. And it's hard to see, but the flag is 1, indicating the first wave is later, is lagged. It arrives after the second wave, and the time difference is 3.125, and the unit is microseconds. Since our sample frequency, due to our sample frequency and the delay number we used, and I changed that, and I switch the 2 signals and change the delay to 200. That actually becomes negative 200 for a delay, and the flag turns to 2. And then we turn to a real receiving signal from the using USRP device. So we sending out a sine wave using 1 transmitter antenna and receive by 2, and goes through the same process and go there. We find out the receiving signals become very distorted and extremely unpredictable. So we had we use a different approach to minimize the impact of that distortion. So the phase difference won't be determined at once. It will constantly find the peaks of the incoming waves, and then gradually incline to a better result, if there is one. And the second part is to do Wi-Fi detection, because we aim for a wireless Wi-Fi source detection. So that's where we modify the WinMe project and program to count the occurrence of each MAC address and show the most active one. And also we modified flowchart to say filter out irrelevant signals and only focus on some specific MAC address. So that's the flow chart, and we really focus on this part. So this block we modify to only filter out and focus on the interested MAC address. And also we do the most active source analyze in here, which is the file sync. We have a outside Python code. So here's the Wi-Fi result. We are okay. This is okay. So that's the setup. It's like connecting to the PC and run the gen radio. And here's some result we are receiving, but it's really hard to say. Okay.
Yeah, all right. So yeah, just to mention, these are just the information of the Wi-Fi package after decoded. So yeah, we can see that from. Okay, so for the AR platform, after given the theta and phi, we calculated from the two signals we receive. We need to update these data into our local server, and from there we do all the calculations to find what's the updated phase difference, and then we want to move the third corner service accordingly. So for the technical part, we use OpenCV and Python to realize this part. And also, just to mention, the Windows sensor library is kind of poor documented. So it was kind of hard to realize that, but that's how we use the gyroscope to do all the tracking after we located the original signal once. So yeah, and then this is the calculation we did on the AR part. So after initial localizations, we update the phi and theta to our local server, and based on the gyroscope reading, we did these calculations just to update the X, Y, Z axis so that we can track that accurately. So for a short demo, this is a stationary demo right now. Let's see. So we're not looking at some Wi-Fi source right now, but you can see there's some there's little noise made by the sensor reading, so it's kind of moving around, but it's acceptable. It's acceptable for us. It's still in the range. And actually, if you where is it?
What do you want to do?
Go back to the. Okay, so if we do the full motion demo. Okay, as you can see, if we move around, that green circle will disappear, and after we came back to the original location, it will appear again. So that's how we can successfully track the location after we initially localize it once. So yeah, and possible improvements on these parts is that if we can filter out the noise from the sensor, that'll be better. And also, if we can adjust the focal length by pixel size, which is the factor we have in the original equations, that would be better for us to get a more accurate result. Okay, so our goals and achievements. Our goals originally would be to isolate and to monitor signals from each Wi-Fi enabled device around the users and to locate the direction of the source, and then to develop and successfully develop an AR application that visualizes the location of the wireless source. But right now, what we achieve is on the right side. So we were able to detect all bands Wi-Fi signals around the device, but we cannot automatically identify the unknown device. For example, if you want to, maybe track some hidden cameras inside the room, we were not able to just find that automatically. You'd have to filter out all the known signals and then just look at the unknown ones specifically. And but also we are able to determine the phase difference between two antennas with one known signal source, so that's pretty good. And our application can track a single source, currently initialized with theta and phi equal to 0, and shows just some noise, so that's also pretty good. And this is strengths and weakness of our project. We explored an implementation with only 2 USRP devices and GUNI radios, so that makes our project pretty easy to be implemented. And our AR platform is usable and can be extended easily, so that's pretty good. But the weakness would definitely be that we have a difficulty in testing without an ideal environment, where only one signal exists. For example, as you can see in the demo, we had we had distorted signals reading, so that's kind of bad. But if we are feeding only one signal source, our calculation were pretty accurate. So another weakness is that we couldn't sync 2 antennas board to get the accurate phase shift. Because we're only given 2 USRPs from this aspect, but we'll seek to implement that in the future. So the remaining steps would be integrating the GUNI radio project with AR platform, just by updating the data we received to our AR local server, and then calculate it and update all the phase angle there. And we'll definitely collect and analyze more experimental data. For example, we'll look at different signal source to see what result we will get, and to see if that might be different from different signals. So our future work. So first of all, our limitation would definitely be the testing environment. But one thing that's also very important is the hardware we're using. In the future, if we can improve our, if someone is also doing this work, we recommend him to use some hardware like a Twin RX USRP, which has 4 receive antenna array. That'd be easy to implement using the DOA library. And by the way, this one can be used to track the missile, so it's pretty accurate. And also our AR method could be improved. Yeah, that's basically that. Any questions?
So I guess what wasn't clear to me is that the first and second part integrated at all, in the sense, are you able to find the angles to a particular source accurately? Because the second part sounded like you were injecting not the Wi-Fi signal but some sine wave or something like that.
Yeah, so like that part is just like so the phase shift. We want to say that. So the Wi-Fi signal is a line code and convoluted with the coding, the QPSK coding. So it's kind of like very hard for us to determine the phase shift based on that. So like right now we are like just like take the baby step to say, okay, how can we measure the phase shift using the possibly most simplest signal we can have.
Right. So is it fair to say that right now you cannot find where the Wi-Fi source is? Right?
Yeah. Yes,
okay.
That's correct.
So the 3 parts are separated. So in your future work, it's not simply GNU radio part needs to be integrated with the AR. It's actually the 2 GNU radio parts also need to be integrated.
Yeah, that's right. That's right.
So in part 1 for the Wi-Fi, what did you have to do over YME?
Because
WYME already exists. So what changes did you have to make to YME?
We add one part here. It's right here. It's the Wi-Fi Mac block, and we change the connection a little bit.
So what does it do? Like what do your changes do?
So after we have that, we can just specify any MAC address we have here. So this output file will only
capture those
specific signals we want to.
So it's basically a filter where you only capture
Yes,
those.
yes, that's right.
So then somewhere you said something about you are currently not able to do the particular like you were saying something about that you cannot locate just the Wi-Fi packets of interest if there are other Wi-Fi sources. What did you mean by that? There was a slide where you were
Oh.
saying something about
Is it right here? So so this is the reading we receive right now. You can see these readings are distorted. But when we are sending just some ideal source, these readings are pretty good. So I was just wondering if we can just have only one specific signals.
And what did you mean by time difference of arrival early on if you're doing?
Okay, so so first of all, if we this is the realistic implement. So if we really want to measure the phase difference between the two USRP devices, they should be synced to a external clock resource, which is an extra hardware, say like a PPS clock resource. So like right now we don't have that, and there's like no connections between the two boards. They both connect to the host PC, but like not with each other. So the time clock we have are like separate, and since they are not synced, even though we try to measure the phase difference, it won't be accurate enough.
Okay.
So it's just like we are so limited on hardware, so it's like the.
But you didn't try to use the GPIO lines between the USRP2?
Well, like I don't think the GPIO will fix it because we really want to sync them, and to sync the two board we need one external clock hardware to do that. So just connecting them with each other won't sync them in clock.
That's not true. But anyway, anyone else with any questions?
Yes.
I noticed that you said you are unable to detect unknown Wi-Fi signals. But in these pages, you said you can have a list of MAC address when you detect the Wi-Fi, right?
Yes.
I'm thinking if you want to try maybe to compare the MAC address to some specific manufacturer, because I believe different manufacturer of Wi-Fi devices have their own MAC address starting with some kind of bits. Maybe that will help you.
Yeah, definitely.
The unknown devices.
Yeah, that's the way we thought we could do. But we didn't have time to do that. But that's definitely doable. Yeah.
Because there should be a library containing the MAC address and corresponding one MAC address to be some specific manufacturer.
Yeah, that's right.
Okay.
All right.
I think
Thank
we are
you.
running a bit behind. So go on, thank you. Who's the next one? Yeah, can you go to the next slide?
Alright, hello everyone. My name is Kian. I'm going to be talking about the REM sleep tracker that I built this past quarter. So basically an overview of what I did and what my specific aims were to improve the existing sleep tracking that we have. Right now sleep studies are very expensive and impractical. You have to go into a clinic, you have to have an appointment, you have to wear all these wires, it's difficult to fall asleep, and it's not good for tracking sleep over time. It's not something you could do on a nightly basis. So these are called polysomnographs, PSGs for short, and they monitor brain activity, so EEGs, eye movements, EOGs, muscle activity, EMG, and heart rhythm, which is ECGs. So it's important to note that the eye activity that's being measured is not like an IMU based sensor. It's actually electric based. So they put little electrodes beneath your eyes and they can sense whether or not they're being closed or open. And additionally, there's some current at-home sleep trackers, and they use movement as an indicator of sleep, but they often have an IMU on the wrist, as it's a watch or some other kind of device like that. And these have been proven to be inaccurate for specifically REM sleep classification. There's also a couple of solutions that have just come out within the past few years that provide sleep tracking through EEG. So there's two headbands, two different companies. These started at around anywhere from $200 to $700. And I'm seeking to create a solution that's more cost efficient and also more comfortable than the existing sleep wearables. Okay, so here's the technical approach. I created a sleep mask, as you can see, and there's a little IMU, this red chip here, that's been kind of attached to the mask that will sit directly on your left eyelid, and it's able to detect these rapid eye movements. In addition, I used a pulse sensor to monitor heart rate, and this is supposed to have long-range correlations with REM sleep. But as I'll talk about in future slides, that wasn't really what I found. And this EEG headband by one of the manufacturers I mentioned was used as the ground truth for these signals. So I'm looking for alpha, delta, and theta waves in that order, which will lead to the beginning of REM sleep, and there's some sawtooth waves that are going to appear there. And REM sleep happens about every 90 minutes, and the cycles typically start around 10 minutes and then can increase up to maybe 20 minutes by the third REM cycle. So I was able to collect data over 21 nights somehow, getting about 2 to 3 REM cycles per night. So I was collecting data from the pulse sensor and the IMU, and then also data from the EEG headband. And so all that data collection was automated with Python scripts, and then here's an example. You can see some direct correlation between the EEG data, which is on the left, and the accelerometer data from the IMU. So right at the spike of the theta wave at around 3:30, and all these, you can see all the waves come closer together. You see significant activity on the IMU, and then again a second REM cycle occurs around 5:15 or so. So when the waves come together and the theta spikes, you see another spike in activity from the accelerometer. So in order to actually make use of this data, what I did was I had to go through manually and label the heart rate and IMU data. And what I found is that the pulse data actually didn't have any correlation at all with REM sleep. So that wasn't actually useful for me, and I didn't include it in the final neural network that I built because it didn't have any meaning for the model. So additionally, the magnetometer data was pretty noisy and it kind of drifted over time. So I figured that the gyroscope and the accelerometer measurements were going to be the best features overall. So what I did was I was able to get 420 samples for the neural network, which was a convolutional LSTM. Each sample was 512 time steps, so I basically subsampled the data, the raw data from the IMU, and used that to create these training samples. So 294 training samples, 63 validation, 63 test. Overall, with this convolutional LSTM, based on the model that Vikrant shared with us, I was able to get these mean scores and accuracies of around 96%. So pretty good considering how messy the data is. So prior work and relative novelty. There's existing papers that cover a convolutional neural network that achieves around 90% accuracy for predicting REM sleep. However, this is using the pure EEG signals. So as you can see here, as the more channels are added up to 11, which is a node of one of these EEG headbands, then you get more accurate results. And there's also studies that have been done with the Jawbone Up, which is one of these activity trackers, which uses an IMU on the wrist. And they tended to overestimate total sleep time and sleep efficiency. And they were actually associated with time in REM sleep, but it's not going to be as accurate as something like an EEG data. So even the state-of-the-art PSGs, as I talked about before, are using the electrooculography rather than an actual eyelid IMU sensor. So that's going to be a lot more expensive than your off-the-shelf part. So remaining steps, the convolutional LSTM that I used, I had 2 convolutional layers and 3 dropout layers. I basically just finished collecting the data over the weekend and started creating the model over the weekend, so I want to go ahead and tune the hyperparameters a bit more, batch size, loss function, optimizers, and experiment maybe with other neural networks. Although he did mention in his presentation that the convolutional LSTM is typically the best one for activity tracking or activity recognition. And I could pursue a couple other different strategies to weigh or sample the data based on what I did. And I think future directions, definitely if I wanted to incorporate this into a more user-friendly device, I would put a Bluetooth chip and a battery into the eye mask, because then you won't have any wires that are sticking out of your eye mask that prevent you from kind of moving around in your sleep. Another issue was the manual labeling of training data. So it was a bit difficult, as you can tell from the slides, to find exactly where the REM cycle is. So if there was a way that I could come up with some software, some script that would be able to do that automatically, that would have been great. Another thing is add training data from multiple individuals. The way that my sleep cycle works and the position of my head, position of my eyelids, my movements is probably unique to me, so I would be able to decrease overfitting and account for more varieties of sleep movement. So I think another thing that could be useful to do with the data is to have recommended wake up and or sleeping times. So based on when you're going to bed and when you wake up, based on how many REM cycles you're actually getting, they could say, you should go to bed at this time, you'll get 3 cycles instead of 2. And yeah, these are some of the sources that I used to get the background information. Any questions?
Okay, thanks. Anyone questions?
Yeah.
How is it powered?
How is it powered? So it's just connected to a microcontroller. It's just 3 volts, and the headband is like micro USB, but its charge lasts the whole night. So yeah.
Is your inferencing happening in real time, or is it recorded and?
No, so it's recorded, and as I said, I have to manually label the data, so that's a bit difficult. Yeah.
Is there any data set that you can use, or do you have just manually train it on your?
Yeah, so I wasn't able to find any data sets. There were some on the heart rate, but as I said before, there wasn't a correlation for my experiment. But there wasn't anything about IMU sensor data directly on the eyelid. There was nothing like that before. Yeah. All right.
So can you move to the next slide?
Yep.
Yeah, thanks.
Alright, hi guys. So I'm Nicholas, and the project that me and my partner Eugene has been working on is the distributed digital IoT assistant. So the overall project goal for us is to build a digital assistant that can take our human vocal command and process it and output to multiple command lists across multiple devices, including like sensors and actuators. So we were able to convert this whole project into 3 steps. The first phase is that we're assuming that we already know what the devices we're trying to interact with, and then we simply try to identify what we're trying to do with it without generating any parameters. And the second phase is that we still give the full sentence including all the information the system wants, and then let the system generate the different like functions, device, and parameters, including when to trigger the different scenarios. And also, of course, the parameters should be included in this case. And the stretch goal, which is the ultimate goal for this project, is to allow the system to dynamically assemble different macro programs across a dynamic device set. Right. So most of the most popular prior works compared to our project are the Apple Siri and Alexa and Google Assistant. For Siri, it has a limited interaction objectives because it can only communicate with that implanted single device only. And for Alexa and Google Assistants, it can allow us to interact with multiple devices, but each time we can only input one single command. And if we want to have a macro programming over a bunch of devices, we have to like forcefully input multiple commands. And in comparison, our work, the DDLTA, it's able to synthesize multiple command lists from one single input sentence, as well as dynamically assemble the macro programs. Right. So here is the flowchart of our project. So when someone speaks a sentence as a command, it's first converted to text, and before passing through the syntactically through the spacing. And then a list of commands is generated, each of which has actions, device, parameters, and conditions. And then all of these commands are put into the next layer to remove those stop words to make sure that only the key information is preserved to be input to the systems. And the final step before we make the output is that we try to process some synonym and acronym processing to make sure that the commands, the words that the user is trying to use can be understood by the system. And this synonym, acronym, device, command list are written by ourselves. Right. So the first layer of our approach is the speech to text. This one we use the general Python speech recognition model, in which we implement the Google Speech Recognition API, which can achieve a 92.5 accuracy, which is pretty good and compared to other APIs.
Okay, so for our next step inside our flowchart, we use a module called Spacey, which basically does the sentence structure analysis as well as POS tagging for our input sentence. So if you look at this example below, if we have a sentence input such as put the cup on the table when Henry walks in, after we input this sentence into Spacey, it gives us the part of speech tagging of each word, which is indicated here. For example, put would be a verb, the cup would be a noun, and on would be an adposition. It also gives us the dependencies between these corresponding words, so that we know that the cup should be a direct object of the verb put, or for example, the word Henry should be something that corresponds to the word walks over here. Okay. So after we have this particular POS tagging as well as our sentence syntactic dependency, then we input this tree into our command recognition function. So we parse our entire command into we parse our entire input into a command that includes four different elements inside our tuple, which are the actions, the device that takes the action, some extra parameters, and whether there is a condition for this specific action or not. So, for example, in our previous command, which is put the cup when Henry walks in, then we would separate our command into the action, which is put, the device, which is the cup on the table, which is the parameter, and this particular command only executes when the condition is matched, which is when Henry walks in. Okay. So then the next step would be stop word elimination. So in normal NLP processing, the stop words are often used basically, so you just check an entire stop word database and see if there are any particular words inside your input, and you just remove those words. However, during our particular project, we noticed that several different stop words that are often removed, in fact, has a particular input key information for the grammar aspect, as well as the relationships between different nouns or subjects within our input sentences. So instead of using a huge database such as the NLTK stop word database, we had to separate the stop words into several different kind of categories that have different and see if they have any functional content. So prepositional phrases such as in and on, off cannot be removed because they might represent a certain parameter, such as turn the light on or turn the light off. However, some other conditions, some other stop words such as determiners, which include the or and, can be removed since these words don't have any specific relationship to our devices or parameters or even actions. So, and the final step would be to check if the words the human input comes into can be corresponded to our device sets. So, since our project is specified to work on a dynamic device text, that means that every time we do this kind of pre-processing, we have to have a static lookup table of the currently connected devices as well as what functions each of these devices can use. So that means that, for example, when the human user says something like change the temperature to 75 degrees, we have to this program has to know that temperature corresponds to the air conditioner, since not all devices can actually change the temperature. And also we have to indicate that the word change represents the function set inside this particular device. So, and one final step inside our entire program is what we call the command generation. Since we know that during our human input, we can say something such as turn on the TV and the lights. And this means that device and parameters can be coordinated with conjunctions, such as the word and. That means that when we're trying to parse this sentence, we have to separate this one command into multiple different commands, which are then passed on to the post-processing downstream tasks. So what we do is that we looked if several devices have relationships between other devices that we call the conjugate devices, and we look at whether some parameters have relationships to other parameters, which we call the conjugate parameters. So for each of these device conjugate device and parameter conjugate parameter pair, we duplicate the command such that each of these devices and parameters have a different command that we can further process into the downstream tasks. So one example would be
it's still the put the cup and the plate on the shelf and the floor.
Yeah. So if you say put the cup and plate on the shelf and floor, then for the final output we should have 4 different commands, which is put the cup on the shelf, put the plate on the shelf, put the cup on the floor, and put the plate on the floor.
Right, so the performance of our system is checked by inputting like 41 pre-compiled commands, most of which are obtained from, let's say, most popular Siri commands or Alexa commands. And then the general accuracy for our system is like 90%, which is okay. And another thing worth noticing is that the latency for different lengths of the commands, maybe you cannot see it clearly. Like this is like 3 until 12. So the latency for different lengths of the commands does not like vary very much. And then we consider that it's a stable performance of our system.
Okay. Yeah, so the strengths of our project is that it has a rather high accuracy, and the latency is rather stable for different lengths of the command. And it's capable of customization, since the kind of command doesn't really matter. It matters whether it more depends on the devices that can be connected to our particular project, a particular module. The weaknesses is that since we're doing speech to text inputs, punctuation may be a problem, and therefore the syntactic parsing during the spacing may also have a problem. And therefore, the sentence structures will also cause confusion for our command generation and command parsing. Okay. Awesome. Yeah. So, for our future works, we want to look into some specifically confusing cases, such as the word width. Since the word width often represents some kind of subclause that provides further clarification for our devices, parameters, or conditions. This kind of condition often causes the spacing module to have an incorrect prediction between the relationships of this particular word, and that of course causes further errors inside our command generation. Yeah. So, and for our stretch goals, we want to look into methods to dynamically assemble our macro programs. So what this means is that we're trying to look into, rather than expressing one command at a time, we're trying to see if we can specify one task that actually corresponds to multiple different commands that by working together can accomplish our particular task. So for example, if I want to say I want to catch the thief, then our program should be able to identify that the first command would be to open the camera, the second command would be identify the thief, And finally, maybe the third command would be something like notify the notify the police or something like that. So
So here are some reference and relative novelties we made to these already existing models and contribution. Any questions?
Yes.
May I ask, how is latency defined here?
Oh, so the latency is defined that it starts from after you have made your like voice input, and then it goes to like processing to text and get processed by our system. And when the final command list is printed out, that's the ending time. Then we just take how much time it takes for these steps happening in between.
Yeah, I asked because sometimes the adversary just waits for many seconds.
Yes. So the thing is that you can just manually set a timeout, but you can also just let the system wait until like it hears nothing. So we choose to use a timeout, but choose to make it like a relatively long time. So basically, the Google API, it has an advantage that once it stops hearing anything, it can start generating commands. So that may save us some time.
You had a question?
So the 90% or so accuracy you're getting, does that take speech recognition into account, or are you just feeding the numbers that you're speaking?
Oh, that one is just that's just after the text and the speech to text, it has another accuracy we mentioned above.
92%.
Yeah, 92%.
Yes.
Say that you do some mapping between like certain parameters to particular devices. I'm thinking that is there cases that you have multiple devices that are associated with different parameters? In that case, how will you mapping the parameter to those multiple devices that has this similar like services?
Okay, so you said multiple devices that can do.
Say like you want to work on temperature, like maybe the person has the central AC, but they might also have a portable like a computer or something. So how are you going to distinguish which one of the device?
So our current system will basically do both. So yeah, it'll be a simple kind of patch to basically if you have different devices, just ask them, can you provide further clarification which device you're actually referring to? Yeah.
Yeah, and another thing worth noticing is that so our command logs the device first, and then attempts to find the action on those devices. So yeah, but these two things like kind of go parallel. So
what's the level of integration with DDFlow right now? Like, is the output that you are doing just plain text, or are you actually outputting any DDFlow?
So currently it's outputting plain text, but I mean, so we asked Joseph, but he hasn't given us
any spec,
any kind of input he wants.
Okay, he's busy. Okay, thanks. Let's move on. Can you move to the next slide, please?
Okay, my name is still Glenn Meyerowitz, and I'm still working on using embedded sensors to recognize weather patterns that can degrade autonomous vehicle performance. So I'm going to start off giving a little bit more background about what are autonomous vehicles and what are different levels of driving automation. So this might be something that some of you are familiar with. So a few years ago, the Society of Automotive Engineers, SAE, came out with this chart to describe the different levels of automation from level 0, which is no automation, so that is a fully human-driven, 1980 Corolla, to level 5, which is something that doesn't exist yet. That's the idea for future full, the golden ticket of a full self-driving vehicle. There's kind of this distinction that exists here in between level 2 and level 3. So 0, 1, and 2, the idea is it's human-controlled, and then the autonomous system is there as a backup. For levels 3, 4, and 5, you can think of it as the reverse. So the autonomous system should be in control, and then really the human is there as the backup in case something goes wrong. For a lot of what we're going to be looking at now, I'm going to be focusing on level 4. And so level 4 is a system where it's supposed to operate by itself within a specific operational design domain. And so what that means is that there's some constraint that's created by the developers, and then within that domain, the system can be fully autonomous. And when it's outside of that domain, the human has to engage and be in control. So this domain can be based on a variety of different factors. It could be location-based, so that's called geofence. So for instance, when you're within a parking lot, you can be autonomous. It can be geography-based. So that could mean when we're on flat ground, we can be autonomous. But if it's slopes above or above a certain grade, then we cannot be. Time of day, so it could only be from 9 a.m. to 5 p.m. Weather, so you could say we can operate in sunny conditions, but we cannot operate in rain or snow, or other conditions that you can think of. And typically your ODD is based on a desire to avoid certain types of environments. So snow is a big one, right? It's very different to operate in Miami versus to operate in Chicago or something like that. And so this decision of operational design domains leads us to the real question for autonomous vehicles is not when they will be deployed, but where they will be deployed. And so this is often a question about unit economics of where is there a business case where you can make money with an autonomous vehicle, and it's also simple enough for your vehicle to operate there safely. So this leads us to the question of what is the impact of varying weather conditions on autonomous vehicles. So what really is an autonomous vehicle, right? So it's going to use a suite of sensors to perceive the world around it. Those sensors will feed data into some kind of central processor, which will determine the state of the world based on that sensor data and its knowledge of the world, right? So the state at T0 and then kind of all states before that. And then as ambient weather conditions change, of course, it's possible that the sensors on the vehicle will behave differently, right? So they could experience degradations or failures. So if you start off leaving in the morning and it's sunny and then it starts raining, you can envision that cameras and other sensors might begin to behave differently, which could impact how they perceive the world and the data that they give you. So when we ask the question, what's the impact of weather on autonomous vehicles, this in many ways really boils down to the question of what's the impact of varying weather conditions actually on these sensors. And so here I have a list of a few different sensors: camera, infrared, LiDAR, radar, ultrasonic, GPS. Obviously there's more sensors, and then a variety of weather conditions: rain, snow, dust, fog, glare, darkness. I guess maybe weather conditions might not be the right word, but varying ambient conditions. And then here's a high-level chart kind of how some of these conditions can impact these sensors. Important to note, this is really just to kind of a first order. As the severity of any weather condition changes, it can have a very different impact on a sensor. If it's a very light rain, that'll have a very different impact than a very heavy rain. And so you can see that a lot of the sensors, particularly we can look at cameras, will have a lot of degradation as soon as the ambient weather changes from sunny and really nice weather. So what is the impact of changing weather conditions on human drivers? So how do we change our own behavior in different weather conditions? And so as I'm sure anyone here who drives knows, when the weather changes, you should, and you often do, change how you drive. So here's a chart that shows as the speed limit increases, when weather conditions get worse, there is a larger increase in how fast people drive from clear weather conditions. So you go 5 to 10 kilometers per hour slower when it's wet or at night than you would if it was clear in the middle of the day. And so this is not only because of how how you perceive the world changes, right? So what you can see is physically different, but of course also the physics of how the vehicle interacts with the world is different, right? So from hydroplaning or skating on ice, the interactions between tires and the ground will be different if it's wet or icy. So what do autonomous vehicles do now? I guess I want to start off by saying, obviously there are dozens at least of companies that are developing autonomous vehicles. Each one has their own path forward, and that's constantly in flux. But to the best of my knowledge, there's currently no consideration for changing ambient weather conditions on how autonomous vehicles operate. So the vehicles have a given set of parameters, and so these can be based on things such as a high-definition map or something else that determines a state function, and that will control things such as what's the maximum speed you're going to take on a road, what could be a turning radius that you feel comfortable taking at a given speed, what's the following distance between you and the car in front of you. but these are not parameters that change as the external state of the vehicle changes, because that's a very difficult problem to solve. And often by carefully controlling the ODD, you don't need to do that initially. So that leads to what am I looking to do on this project. So this is what I discussed last time. So to create a label data set, database of images that show a range of different weather conditions that a car or vehicle may experience on the road, train a neural network to identify and classify the images and video based on the weather conditions, deploy that to a small embedded device that can use a camera to emulate one of these autonomous vehicles, ideally create a way to vary weather conditions in a custom environment, and then assure that the system properly adjusts some kind of finite state machine to account for changes in these external weather conditions. So what are we looking to do technically? So this is an implementation of VGG16, which is a well-known and used convolutional neural network for image recognition. The only, I guess, not the only downside, but one of the downsides is very big, so it takes a while to train and then to do inference on. But so you take your images, scale it to 224 by 224 by 3, and then you run it through these series of 16 convolutional layers. I'm implementing it in Keras on top of TensorFlow. The data set that I have now is about 1,300 images of dark conditions, rain, snow, and dust. And then one thing to look at, right, is how are you going to predict the label for a given frame? So this is, of course, something we were actually just discussing in the last lecture. Because for my model, it's trained on individual images. Is there a way where you can get a higher accuracy on a prediction of a video than you would potentially on individual images? And so you can use a fusion scheme to more accurately predict what the label for a video is. So I'm using classifier fusion based on this. So we'll just take the average of the past n number of frames, or n is going to be whatever hyperparameter we have, and then we will just do the argmax of those labels to figure out what do we want this, the label in this frame to be. Of course, that does run into an issue where when you first start, you don't have that historical data, so you might not be as accurate at the beginning, which of course can then impact your accuracy down the line, but what can you do? Data set for ambient road conditions. So here are the 4 categories that I have. Rain, snow, dust, night. These are I got from skimming images from Google Images. I'm just downloading as many as I could. I guess not as many as I could, but as many as I reasonably wanted to. Spent some time determining the optimal learning rate. And so I'm looking to, or for my training, I use between 10 to the negative 5th and 10 to the negative 3rd. If you go beyond 10 to the negative 3rd, then you are most likely going to overfit your data. So the training results that I have right now, I'm still only getting about 80% accuracy, which is less than where I want to be. And so that's something that I think I need to spend a little more time going through and pruning some of the images that I got from Google Images, because I'm sure some of them are not correct, which is unfortunate. It takes about 60 hours to train. It's got about 50 epochs on my laptop, so like I've only been able to go through it 3 times. So I'm hoping to get one more training session in for.
Well, why don't you use the Google Colab?
I guess I'm just not as familiar with that.
Okay.
So yeah.
Well, you get free GPU.
Well, I'll get that started. We'll see. Yeah. So on my laptop, it takes quite a while, which is not great. Remaining milestones is to achieve a higher accuracy. So I'm looking to prune the data set a little bit more. Just this past weekend, as anyone who's here knows, it was raining, which was unpleasant, but I actually got to record some good real-world data in my car, and I'm looking to deploy that on the Jetson Nano for real-time inferencing. One thing to note as well, when I do the inferencing on my laptop right now, very much not real-time. Yeah, it takes a little bit under a second per frame, so not real-time. One interesting weakness of this, which is the last thing that I'll discuss, is the fact that anything really that's neural network based is prone to adversarial attacks. And so there's a pretty cool paper and video that came out by the team at Tencent Labs, where they practice doing adversarial attacks on Tesla, on a Tesla car. So Tesla is the only company that I'm aware of that uses cameras for any kind of weather detection, and they just have something called Auto Wiper, where they have a camera on the front dash, and if it sees what it determines to be water, it will turn the windshield wipers on. So it's not used to adjust any kind of finite state machine. into the vehicle to adjust behavior. But they were actually able to literally display this screen to what any of us is nothing, and that is capable of tricking the camera to think that it's rain. And so that's just because of how the neural network works on the camera, just in how it's trained. So obviously there are adversarial attacks that are possible as soon as we add automation to vehicles. So sensor fusion, combining multiple modes is kind of the best way to avoid that. If you're only based on cameras, then that's a little harder to do. Disclaimer, anything that I've said only represents my views, FYI. References, any questions? Yeah.
Yeah, so how big was your data set for training all those four scenarios?
Yeah, so I have 1,300 images total, give or take. So that's divided, give or take, evenly between those. Yep.
Is your testing data set also like from those images?
Yeah, so I guess it's 1,300 images that I then divided about 70% to training and 30% into, or I guess split between a validation and test. Yeah.
And then, like, when you're training it on BGG, are you just like changing the last few images? Because like if you do it that way, it could probably like take less time than 16 hours. So you can just like use a pre-trained model and just do transfer learning on that. It might help you.
Yeah.
I'm not sure.
Yeah.
You could actually like break it down to.
We can chat more offline.
Yeah.
But yeah, I'm not retraining the entire thing. So I am using a pre-trained network. But then I guess, I'll have to take a look back and see how much am I retraining. I don't know off the top of my head. I have to look at my code.
How do you calculate the accuracy? Like using cross-validation or use some data set as training some else?
Yeah, so I just downloaded a large number of images from Google, and then that's split between all the different sets. So it's on that.
So do you have a separate validating test and a separate test set? Because it sounds like you have already tested, and now you're going to iterate on it, so it's no longer a test set. So the way you should do it is your test set should be done once at the end. Okay.
Okay. Yeah.
Validation training and validation, and that you do by whatever and cross validation and all, and you optimize everything. Sounds like right now you have used all your 1,300 images, so now you're going to be iterating on it. So your test set is sunny. Test should be done on something just once, exactly once, and that.
Yeah. So what I'm looking to do for the final test is going to be either data that I recorded this past weekend from my car or from a small. If I have time to. Yeah. So it'd be a fresh set for the real test. Yes.
Okay.
Yeah.
Can add some feedback because the system will send a different command to vehicle. Depends on different weather, right?
Correct.
How can we clarify that the command is suitable for that weather?
So the idea is that you'd have some kind of state function in the vehicle, and then that state function would determine some wider parameters of how the vehicle operates. And so let's just take maximum speed. So normally your maximum speed for your vehicle is maybe 60 miles an hour. And then if you determine now it's raining, then you can drop it to say 50 miles an hour. Or if it's snowing, you could say, okay, now we're only gonna go 40 miles an hour or something. So you'd have a way of altering certain parameters. So it's not necessarily that that would control if you say it's raining, that wouldn't control the vehicle itself, but that could be used to kind of choose parameters of how the vehicle operates.
That's cool. Okay, let's move on.
Yeah.
Now could you move to the next slide?
All right, hi guys. I'm Michael, and this is Vyacheslav, and we're doing real-time SCMG recognition for remote control of personal devices and IoT. So to begin, our overall project goal is to just create a gesture recognition algorithm for purposes of interfacing SCMG sensors with personal devices and IoT. We want to propose a specific set of gestures based on trade-offs between accuracy and ease, and what we want to do is we want to capture gestures that are convenient and natural, specifically towards natural typing movement. We want to develop a feature extraction algorithm and implement our neural network to capture those gestures and demonstrate translation of the algorithm through an Android application. So today, there's not any popular methods of interfacing human-computer interactions with SEMG signal analysis. Firstly, traditional methods of SEMG signal collection is very hardware intensive. You have to strap on a bunch of electrodes, so it's not very convenient for an interactive environment. Secondly, commercial products like the Mile armband they're portable, but they're less accurate. And what we want to do is we want to branch off that idea and make it into something that we can rely upon to interface and create essentially a new framework of communication between people and their devices. So we want to capture those typing gestures and reliably translate them in some way. So the novelty approach is mainly within the gestures that we're capturing. These have not been done within any prior works that we've come across so far. So a characteristic of all the prior works that we have went through is that they all maintain a dissimilar set of whole hand gestures, such as like a closed hand, open hand, a tap, or some large finger sweep. These all magnify some kind of noticeable output within the Mile armband. And what we're aiming for is a very subtle tap or gesture, which we'll show later on. Recently, real-time classification of these gestures have become more of a thing. So papers have been working on testing different neural network architectures and like CNN, GRU, and all those different architectures. They also test with different features such as frequency domain, time domain, and a mixture of both or neither. And so that's how we based our model on, which we'll get into later as well. And the biggest prior work that we came across was the NinoPro EMG database, which is essentially the Mile armband standard for signal analysis. And this was captured with 2 Mile armbands, and it still does not contain our gesture set. So just to show a visual representation, the high SEMG amplitude motions are the whole hand gestures I'm talking about, such as a closed hand, open hand, a tap, or any other large hand movements. And the NinoPro dataset has this one section of finger movements that are called extension, flexion, and adduction. But these are still considered very large compared to what we're trying to capture, which is just a subtle tap or an extension. So we will be focusing on our gesture set within this design. And for our project, we kept the Mile armband in this location. This was where we captured the highest output from our hand. And so we kept it on our left arm throughout data collection and interfacing and so on. So the gestures that we're capturing, okay, so it was a GIF, but just to show, the tap gesture is just a tap of that key, and the extension is like reaching for that R instead of the E. So then we're trying to catch these subtle gestures within natural typing movements.
Yeah, and for these gestures, we collected a data set of almost 100,000 samples. Not all of them were used in like final training process, but this is the whole we have. To process this feature in real time, we use a sliding window approach. That is, all incoming data is divided into segments of fixed size. These several segments comprise a window. Features are extracted from window. These are time domain features. We use 6 of them. Then the first segment is popped out the window, and a new one is appended. Features are extracted again, and this process is running in the loop for some time until all of the features are processed. We apply above mentioned feature extraction algorithm to manually classify that data and then feed it into neural network. Architecture of our neural network you can see on this slide. It is pretty simple. The important part of this is post-processing in real time, because output of our classification algorithm is stored in special array of fixed lengths. And if the number of hits in this array for some gesture exceeds some threshold, certain threshold, we print it to the output. And the thresholds are manually set for each gesture individually. This allows us to greatly decrease the noise in real-time processing. Let's talk about characteristics of our implementation. This is the confusion matrix for all of our gestures. They include 5 tabs, A, F, D, S, A, and space, and extensions R, E, W, and Shift. While this while these values are acceptable for our
recognition algorithm to work, if we apply above mentioned filtering algorithm, we had to reduce the size of our gesture set because there appeared an issue when you do an extension on certain fingers. You go through a lot of intermediate states, which are not so easy to filter, and they're easily confused with other gestures in our set. So this is the final confusion matrix, which is used in our application. And the important thing about this is this value. So KD on the keyboard is often not recognized, as you see here. But actually for our real-time implementation, it is not important, because for the D key on the keyboard, we have the lowest threshold. So we have to have less number of hits for that particular key. Here you can see how we map keys on the keyboard to our gestures. And yeah, we want to show you some demo of our application. This works. We had to add some music to it. So we basically check that connection is made, and now we try to type. So we can tap on the shift, and it is holded. Now we type in uppercase. And as this one shows, you can sit on the couch and type from there. So let's draw some conclusions and mention future directions for our work. We now presented a new...
Hi everyone, it's Gary Nixon here with Managing Weather Information Service Issue Planning Outlook on.
We present a new feature. We presented a classification algorithm for a new set of gestures for my armband. We mapped 7 distinct gestures to 9 keyboard presses. Worst case latency of our real-time operation is 600 milliseconds, so you cannot type faster than that. This is our bottleneck. Strengths of our implementation is that it can be used. It is portable and can be used anywhere. But major weaknesses are that firstly, position of my armband should be fixed on this point through the whole experiment. And another one is that it requires really low muscle noise, because our gestures have a low amplitude, and this is why you have to have your hand rested. Though, as we think now, it can be fixed by applying some filtering algorithm. We think it is possible. We also saw an article which described how to make inferences from my armband position independent, and this is one more possible direction for us to have. And considerably another way to think of it is to implement a new SMG hardware to read AMG signal from the palm itself. We tried it, but actually in real life it takes so much time, and we couldn't fix it to the end of our project. So to conclude with this quarter, we have to complete website, we have to update repo, and we have to update, we have to return our hardware. This is our work breakdown. Basically, we both did all the tasks. Yeah, references, and thank you very much. Are there any questions?
Yeah.
How exactly does the
Oh, so you want to talk about there's just a SEMG sensor on it. So there's five small segments and three larger segments. They capture 8 total channels, and we'll just file that through Bluetooth into our Android devices. That makes sense.
If somebody in this room is not familiar with this term, AMG is an electrical signal produced by your muscles when you contract them, and SMG is a surface AMG signal, and you can capture it with this my armband thing.
Yeah. Well, it's based upon your muscle contractions, which release some kind of voltage through your body, and that captures it.
It is by signal. Yeah.
Yeah, it's by signal.
So is this signal like dependent on subject, or it like varies from subject to subject?
Well, we only captured on us two, but SEMG should slightly vary between different participants. So in the future, that's why we say we've gathered on a more diverse data set.
And it will also vary with humidity and stuff like that, because right? I mean,
yeah, absolutely.
Did you look at gestures other than tapping? Like, for example, I was thinking sliding and these kind of gestures.
Well, it's just that it's very cumbersome to capture these data sets in general. So we just focused on these taps and then the extensions, but we didn't really test the adduction.
So I was thinking for this could be a great thing for things like TV remote and all, changing the channels, sliding.
Yeah.
Those are probably more natural motions, right?
Yeah. Well, we also kind of assumed, we kind of correlated that with just there's already an implementation of my armband where you use your entire arm to slide, which is a lot more inconvenient, I guess.
Yeah, exactly.
But yeah, we didn't exactly look towards this bottom portion.
Okay. Anyway. Cool.
Mm-hmm. Any other questions? Yeah.
When you were testing it, you were already in the training data set, right? Did you try it on someone who actually did not train at all?
Oh no, we just tested on ourselves, and yeah, that we didn't really look outside.
Let's move on, because I think we are spilling over. Thanks. Can you move on to the meeting?
Okay, so our project is called MR Wearable, and I'm Vivek, she's Yo-Yo, and he's Swapnil. So what's the main problem that we are tackling? So in a MR world, using the bulky VR headsets that are equipped with all these fancy stuff like complete GP, IMU, and equipped with the cameras is not very feasible, as you cannot interact with the real world very freely. And in those bulky headsets, the sensors like those cameras for head pose estimation are pretty redundant, because you can get good accuracy with just the IMU based head pose estimation that we'll be solving. And because of these redundant sensors, there's some amount of latency that we noticed when we work with the VR sensors. And also one issue is that they require a good amount of computing power for making the application side. So what we are going to do is use just a single IMU unit for the input and the feedback to get the accurate head pose. And also using this head pose estimate, we are going to build our own binaural audio from a mono-aural sound, and improve the head pose estimation using both analytical and ML model that you'll be seeing right now. And that's it. So this is basically how our model is. So we have these wearables with the IMU in just one earphone, and we take this accelerometer and gyro value, feed it to our head pose regressor or classifier, and then get the estimate of the elevation and azimuth, using which we use a HRTF kernel and generate the spatial audio filter bank, and then generate the audio for both the ears at once. So what essentially we do here is do the head pose estimation using both Kalman filter and machine learning algorithms. So current state is that we have implemented a Kalman filter and all of this part, and even the ML head pose estimation. We have also implemented the human activity classifier, which can be used in a situation like when you are having the MR platform and you are walking around. So it gets to know that yes, you are walking around. So it helps the
visualization part as well. And we have generated the spatial audio, and currently we are using a VR headset to demonstrate the binaural audio, but it can be done without this part. So going into complete MR domain would mean replacing the VR headset completely. So as Swapnil discussed the technical approach last time, we collected the entire data set by ourselves in the lab using these labels and using a OptiTrack ground truth, and as well as a laser finder for the ground truth, and we had a total of 1266 frames and 3 different types of targets. So this is what we did for the machine learning part. So initially what we did was taking the slice data, making it completely subject agnostic, and then binning it into like 40 degrees. So initially we binned them into 20 degrees, but because we have limited data, we couldn't estimate correctly for all the classes. Then we binned it to like 40 degrees, which we later on proved that it is like almost the accurate range of what human localization of sound is. And we use 797 frames. So when we select these frames, it means that if a subject is selected, his entire frame or the entire sequence is selected. We did a 3-fold cross validation and 90 train and test 10% data set. We used different models and finally stuck to XGBoost, which initially gave us 42%, but after tuning the hyperparameters such as the regularization parameter, learning rate, and even the number of estimators in it, we got an accuracy of 75%. But then we realized that our data is having like huge data imbalance in the classes. So then we use something called a SMOTH, which is synthetic minority oversampling technique, and we use not one but multiple of those techniques to try out which is the best. And then we got a significant improvement of over 90% using SMOTH as well as hyperparameter tuning. And as professor mentioned last time, classification is a bad metric to check the accuracy. We went on to calculate the MAE and RMSE for the performance analysis, and then once we were satisfied with the elimination part, we went on to do it for the azimuth part as well. So for the technical approach for justification of our models, what we did was to take an off-the-shelf sensor of Wearable, exactly the same sensor, as we couldn't connect the Wearable with the PC directly. So we brought off-the-shelf MPU9250, which is the same sensor in the Wearable. And we also showed that in VR, how would we generate the binaural audio. So currently these two are different systems. Here you can clearly see and visualize where the sound is, and also you can visualize where your head is pointing towards. I'll just show you the demo in a while. And in the VR part, it's like there's a sound source which you can pick it up and move it around, and you can hear the sound wherever the sound source is. So the VR part was implemented in Unity, and this portion of the demo was implemented in MATLAB using Kalman filtering. So our success metric was to show that we exceed or at least replicate the head pose estimation that has been achieved currently in the literature using the Wearables, and get the almost the same accuracy of human activity classification in the literature, and achieving like this achieving the range of error within the human localization, sound localization range. And then we want a minimal latency in rendering the audio. So these are our results so far. So as you can see here, with the Kalman filter, we got an error of 8 degrees in azimuth, and elevation we have just 5 degrees. And in our machine learning part, we got a error of 17 degrees. All these errors are mean absolute error, by the way, and 7.5 in the elevation plane. So we have also plotted the RMSE values, if you can see it. And this was for the HAR part. We got an accuracy of about 95% using cubic SVM, and we didn't stop here. We also trained the shallow neural network, which was like one layer neural network with 15 neurons, and over there also we achieved like about 95% for human activity classes, in which we didn't restrict ourselves to the activities only with head. We tried walking, running, jogging, and jumping, turning around, and even activities like falling on the bed and sleeping on the bed. So yeah, and this was for justifying that the human sound range is within the 40 degrees part. So multiple test subjects, including Swapnil and Yo-Yo, tried localizing a sound source in the atmosphere, and then we got the exact point where they're pointing at, and then with the error measurement we could find out that the median error is about 40 degrees, as we pointed out earlier. So I'll just show the video. So this is the part where you can see that the Swapnil's head, he's moving it. Is this the one? Yeah. And then
I'll play the second video if we have time. Like,
sure. Okay.
Let's show it. Let's show it.
Okay.
Let's show a little bit.
Anyway.
So this was the VR part.
No, wait for me to pick up. So the green boy is a sound source. Well, anyway, so if you put it on the right ear or the left ear, and it will sound different. So the spatial audio is implemented in Unity with the vision. Stop it first, okay? Sorry. This one. Okay. And here it comes to the prior work and the relative novelty. So the first part is head pose estimation, and there are papers that they use two wearable sensors to do the head position estimation, and they have some good results. But our novelty is that we only use a single inertial sensor, but we achieved the good accuracy like them, and even better results in the long noisy movements with the camera filter and the machine learning. And the second part is activity recognition. So because we use the IMU in the Wearable and Wearable as a new device, there was limited work on it. But the literature we find, they use sensor fusion to reach the high accuracy here. But in our case, we didn't use sensor fusion, but we also achieved the accuracy as high as 94.6 and 94.25%, using respectively the CSVN and the single neural network with 15 nodes. And as for the audio part, when we try to fuse the head inertial data and the binaural audio, and we built a demo in the VR headset, but we also proved that using the MATLAB, we think we can also create the binaural audio, and the effect is good. So it provides more possibilities in the mixed reality, because we don't need to use a bulky VR headset. And in conclusion, our work proves the state-of-art performance in both head tracker and the human activity recognition. And we also prove that we can implement the binaural audio by a single sensor, independent of the VR headset. And currently, our main weakness is that we haven't test this in the exact sensor in the Wearables. But it is theoretically the same because we use the same sensor in it to build the testbed. And here are the contributions of us. And is happy to work together. Okay, thank you. Any questions?
So, I don't quite understand why you had to fake the variable sensor.
Also, like we try to when we try to get data from the variable in real time into a computer program, so it was spitting some random values, and then we contacted the devs, and then
They are
said
trying
that
to fix it currently.
there's some problem in the computer API, and they're
Mm.
trying to fix it. So basically, we use the same sensor for the demo that we just showed in real time.
So HRTF is basically a head relation transfer function. So what it does is it has a multiple angles that it so it's kind of a hash table, I would say, where there are fixed number of angles for which they know exactly what would be the filter coefficients for each ear, and basically if that angle is given, then there can be a direct filter extraction. But for our case, as we go for a continuous motion, what we do is we take the HRTF kernel, then we extrapolate it for that particular angle that we are supplying, and then we build those two finite impulse response filter banks, and then using the single audio track, we generate two audio tracks and play it to the ears simultaneously.
Let's move on. I think we're really short of time now. So, okay, thanks.
So today we'll demonstrate what is WebAssembly again. First of all, something detail. So WebAssembly is a binary code for a virtual machine, basically. So in general, what you write is whatever the language you choose, Python, C, R, or Go, all those stuff will be sent to your machine, and the machine only reads binary code. The wisdom here is to sort of one level up to your machine's binary code. So everything you write first transfer to wisdom first, and then to read by your machine. So in original use, that Webassembly is used for web design, and it is used within the browser. For instance, most of the browser we're using the JavaScript environment. So when we use a compiler called mscripten, which is here name is EMCC. So it is a compiler, basically transfer the WASM to your C code, or C++ code to the WASM. However, the output have two files. One is the JS file, and one is WebAssembly code. So the JS file here is used to set up your environment in the JS environment runtime, I would say. And that's how your runtime can run your WebAssembly. Well, however, However, there's another use that we can use the WebAssembly out of the browser, and which we will talk about it later. And that's introduce our project objective.
Yeah, so for the objective, so we firstly want to, since the WASM is a very new languages, and we want to test the current WASM compilers first, and also the runtime for a non-web WebAssembly. And then we want to produce a summary of the current state of the WebAssembly. And then we want to implement some sensor read and write with WebAssembly on different system environments, like the Windows or Apple or the Linux system. And also we want to implement some edge devices communication using WASM. And non-web.
Okay, so here's non-web environment. So like I said, those three are sort of very critical for non-web environments. The first two are compilers. The first one is a well-built compiler to compile C or C++ to the WebAssembly. The second is LLVM, also you can know as the clone. The clone compiles C to the WebAssembly. Those two are currently supporting WebAssemblies. And the third one is, again, like I show you, just sort of bring the the browser out of the browser. It gives you a JavaScript environment to run your WebAssembly code. and this one is the standard that like you can use it out of box. So in this project, we sort of experienced those two later on. And that's the overview, like you said in midterm. So again, we narrow our target down to 4, which are here we built successfully on our devices. The Webassembly was the first priority. However, we sort of shift our first priority from the Webassembly to the Western time because the Western time right now is only runtime supporting the white side, which I also will talk to you about later. All right, so yeah, here's the white side, WebAssembly system interface. It is not something like bundled with one of those runtimes. It is a general concept because it is interface. The reason why I need an interface is in the picture here, if you have a user application running on your devices and there's your system, for instance, your file system, you cannot just randomly write and read your file system on like any occasions, like any reasons. You have to talk to your kernel first because the kernel acting like a boundary between any your application to your system core like file system, because the file system is really sort of critical and sensitive to security, I would say. So the WebAssembly interface is like function like a kernel. First of all, you got a C file and transfer it to the WebAssembly code. However, those are your runtimes actually. Different runtimes has different methods to talk to different like your operation systems. Well, for instance, you have a C code, and the C code know how to communicate to one of those 3 application systems using different system calls. Well, however, Websem here, the Websem code itself doesn't know how to do that. It needs the system interface between your code to your operation system. That's why we use the Websem. Again, in later this project, we use the terminology Websem reference to the Websem runtime WebAssembly system interface core, which is designed specifically for the Websem time. And the Websem right now works like a sandbox mode, which your Websem runtime gives your Websem code to the Websem interface, and the Websem interface represents a agency between your system and your code, so it can handle your whatever you need to do to call specific system call and communication with your devices. Right.
And here we have a overall summary of the platform where we test the complete compilation and the execution. So for the Raspberry Pi, which is using an ARM v7 architecture, this one is a 32-bit processor, so the compilation and execution cannot be run on this device. But for Pi 4, he changed the processor to ARM v8, which is a 64-bit processor. So we can use like Webassembly, which is a runtime provided talked before, to execute our code. But for the compiler, they doesn't work on the Pi. I think they may not, they don't support ARM so far. But for the Mac, Windows and the Linux, they works fine for compiling and execution. Yeah. And for the compiling, we have several kinds of code. So all of the codes are primarily programmed with C, and then we compile it to Webassembly. And first of all, we have a code say. It's just a test code provided by the Webassembly time, which is official runtime. And this one just use some printf or cout to print some character on the terminal, and this one works fine for all the systems. And then we have some hello world files This one uses a standard in-out and quite similar to Coil. And then we try some math functions, and we like compile for Raspberry Pi. We compile the code at the PC side, and then send the code to the Raspberry Pi, and this code can also run on Raspberry Pi. So yeah, so math is fine for all the platforms. And one key function is read and write function. This one is like we want to read some files, and we want to write something to another file. But this one, it works on the Mac, Windows, and Linux, but it doesn't work on the Raspberry Pi. I think mainly it's because the runtime currently they don't support the writing and the reading functions on the ARM-based processor.
So, right. So the last one is what I taught for the Wi-Fi SDK 8, which is the system interface designed specifically for the Western time. And we was able to use this SDK to communicate with low-level system call functions, such as open write and something like the make directory as well.
Mm-hmm. And some details on the different platforms. So for the Raspberry Pi, we can make ARM version 8 work. So, but the compilers of EM SDK, Clown, and Rust, they don't support Wasm compiling on ARM-based devices. And for the runtime, the Wasm micro runtime and Wasm time, they don't support ARM yet. But the Wasmer, this one just supports the ARM architecture just 2 weeks ago, and but it's not fully supported. So it only supported for some functions like for computation, but the read and write is not they are not working yet. And we also directly wrote some WAT file, which is like writing assembly code, the kind of text format of the Webassembly, and we can make it run on the Raspberry Pi too.
Mm-hmm. So in the computer side, I think it feels a little bit easier. So for the first one, the Whammer, we was able to follow it. This is the first run now that we try out on our PC side. So we follow the guideline, and we successfully built it on our Mac and PC. However, it does not run anything yet. It's gives out an error saying it's failed. So we stuck into like for a few weeks, and then we jumped to the next three. The Webassembly and the Webassembly time is pretty similar. The Webassembly and the Webassembly time is well built compared to the other two. And on the PC side, everything works fine until we try something really low level on the Ubuntu. For instance, we try to configure our USB port, and which we did yesterday, like we successfully yesterday, and it gives us some signal back, but signal seems to be unreasonable, and we can talk about that later. So the Webassembly here also, again, tough time on building the Webassembly on the PC. After fixing some error, we successfully built it. However, it's also didn't run for the Webassembly file yet.
And finally, our conclusion and the future work. So we have done at the PC terminals, we test all the runtime, and we are able to compile C, C++, Rust to Wasm and make them run. And also we are able to read files and I/O pins in a Linux system. And on the Raspberry Pi, we can write function in WAT and compile it to Wasm and make it run with a Node.js. And also the Wasmer can be installed, and we can use that to run some computational functions. And for next step, we want to be able to read and write sensors through the system file on Linux-based PC. And then on the Raspberry Pi side, we want to using some edge device computation. So we want to send a WASM file from the PC to Raspberry Pi, and the Raspberry Pi run the WASM for the computation purpose. Yeah, pretty much it.
Yeah. Yes. Any questions so far? Yes.
Do you know any real-life applications that use
Real? I don't know the specifically, but it's meant to replace the JavaScript.
Yeah,
So it should
is
be.
supported on all the browsers, but I don't think any of the apps are currently using it.
Right.
Yeah.
But it's kind of supposed to be in the transition.
Yeah, you want to replace JavaScript. So.
It was designed for web design only, actually. It's none of the
For games and all,
yeah,
actually.
yes. For image. Anything else?
It's mainly because the issue with the runtime. So they only support like 64-bit processors, and yeah, I think they didn't like works on the 32-bit processors. Yeah, processors.
Okay. Yeah. Thank you.
Thanks. This is the last one. Next, you.
Yeah, it's me.
You should probably be the last one.
Yeah. So my project is a pedestrian alert system using Wearables, and for the overall goal. So first one is the audio information to recognize the approaching cars and their direction. And in this project, what we do is we record audio information with 2 phones and 2 microphones, and then analyze the audio file offline. And then next step is extract the IMU information to determine the position of user's head. And we should be able to design an Android app to show the position of the head. And that's for the second one. The third one is develop a mechanism to alert the user if the user is not aware of approaching cars. And for the hardware setup, in this project we use 2 phones, Samsung Note 9 and the Google Pixel 2 to collect audio information. And the reason is that the Android phone itself cannot handle the multi-input. So basically, the Android phone cannot split the input in a good way. So that's why we need to use 2 phones to collect the audio separately. And we choose the quality to be 44 kilohertz because we wanna increase the number of samples in a single frame. And since we are doing it offline and collecting the audio information separately, the synchronization is going to be a critical problem since the latency between the 2 microphones is very small. So the microphone is about 1 meter away from each other, so the difference could be 3 milliseconds. That's why the synchronization could be a critical problem. And for the collection information, we record our sample at a campus garage, and the distance between 2 microphones is approximately 1 meter, and the car is 30 meters from the recorder. So that's the algorithm we're using in this project. The feature's name is called non-uniform binned integral parallelogram. So basically what it does is it equally divides the frequency scale in order to capture the variation in spectral energy at the lower end of the frequency spectrum. So basically what we do is we set a frequency threshold here, and what we care about is the left part of the frequency, left part of the sample, because like the car noise is basically around 200 hertz, which is at low frequency. That's why this part is what we mainly focus on. And for the lower B here, so after we set the threshold, we evenly divided this part by B beams, and this part is just capital B minus lower B beams. And in this project, we choose the small b to be 18 because we want to get more information from this part, and the larger being just 20. So basically, this part is divided into 18 parts, and this one just 2 parts because we don't really care about the high frequency signal. And the first step of this feature is to perform a FFT of your time domain frame and obtain your frequency domain sample. And after you get that, you perform what we call normalizing its magnitude squared. We use the equation below to get it parallelogram. And then after you get, you should carefully set your capital B and the lower B value to make sure your algorithm perform well. and then you do integration of each thing to get your final output of your vector. So after you perform this algorithm, you should get a feature of 1 times capital B size of vector. And frame choosing, so what we choose in the project is a 100 millisecond frame. We actually compare a lot of different frame, 20 second from 20 second to 20 millisecond to 200 millisecond, and we just find that 100 millisecond works best for us, and we choose 2 milliseconds as our slide window because the time difference between the two microphones is very short, so that's why we choose a very small slide window. In the original paper, what they use is a 50 millisecond slide window, but it doesn't work in our situation. But small slide window means a lot of computation, and that's something we should focus on when we transfer this to the real-time calculation, the computation latency. So we compare two, after we get our feature, we feed our feature to the tree model, and in our project we actually test two models. One is one class SVM and one is isolation first. But when we test the tree sample with its own model, the stability for the stability perspective, the isolation first actually works better than the one class SVM. As you can see here, the one class SVM actually have the upside down part, so of its own train sample, so which is something we don't want in our project. So that's why we choose the isolation first. And in the original article, I think they choose random first as their train model. And for the IMU part, so this is the software I borrowed from the Brian one. So as you see the part here, the output of this part is actually the angular acceleration of your head position. But what you should do, what the information to provide is angular acceleration is not the position of your head. So what you should do is perform the integral of the angular acceleration over time. But since the noise of IMU unit is really high, so that's something we should focus on in the future development. So for the alert mechanism, ideally, we can do everything in real time. So first thing we do is we get the information from IMU unit and get the position of the head. And if your head is toward front, and then we just deactivate the alert system to save power, because actually we just say you are aware of what happening around you. But if you lower your head, we assume you are using your phone, you play your phone, you just browsing some website, and then that's the time we activate the alert system. And then we use the microphone of Ethan's Wearable, if we can do that in the future, to collect the audio information and send the stereo channel information to the user's mobile phone and do real-time analysis. And then if car noise is detected, we just perform the direction detection and tell the user the direction of the car. And here are some results from our algorithm. The first one is the synchronization. So what we do is when we record our audio information, we actually use a tone generator to generate a 1 kilohertz tone, and after we run the FFT of every time frame, if we detect a high energy at 1 kilohertz, we set that to be the first frame. And in this example, the time difference between your two phones is about 0.5 seconds, which is pretty reasonable. And then this is the result of the car noise detection. We test our model with some other audio sample other than the training samples, and even though the performance is not always goes to 1 after you detect car noise, but it's pretty robust for right now. And if you just use a sample with some random noise, the value always goes to -1, which is not detect the car noise. And this is the evaluation we use to do the car direction detection. So one part which we notice is that even though we collect the left channel sample and the right channel sample as the same environment, with the same tone generator. Once we run the sample with our model, so the wave is not the same. I think that's the one possible reason could be the phone we are using is different. The microphone, the noise is somehow different from each other, and another reason could be the robustness of our model training. So the sample quality and the system building have some like robust problem, and that's why we are modify our parameter of like frequency threshold and the like capital B lower B to like improve our performance. And the best we can do for right now is making the right car direction detection with like find the time difference is about like 7 milliseconds, which is still larger than we expected, but so far that's the best performance we get. And the remaining step will be collect more samples to train the model and use more test cases to like try to improve the robustness of this system and the computational report. And one strength of our project is like so since the user have the basically human when see stuff with two eyes, they have the angle of 180 degree. So that's why this project doesn't require very good accuracy of the angle detection. And so by that reason, we can cut the microphone from like 4 or 5 microphones to just 2 microphones to make the device more portable in the future. And the weakness would be since we just have 2 microphones, we cannot tell the car is from the front or back. And another thing is that since we are doing this offline, and in the future we should transfer this offline analysis into real time. And since we are using a very small slide window, the large number of computation could have a large latency, and that's something we should focus on. For the future direction, first one is that when we train the model, we should collect more sample of various cars and various environment. So in our project, we just use one car model under one environment, which makes the system is not very robust. And the second one is modify the model parameter, such as the frequency threshold, frame size, and slide size. And we also to be able to transfer this analysis into real time, one possible solution is like use a PCB board, use a specific PCB board which can take 2 audio input separately, and can group the data and send the stereo audio file to the mobile phone via Bluetooth in real time. That's something maybe should be developed in the future. And the third one, the last one is like to determine the position of your head, you have to have a very good sense of the angular acceleration of the RMU unit. So maybe what we do is design a filter to filter out the noise of the RMU unit, and then perform integration to get your head position, or switch to other device to get your head position. Yeah. Any questions? Yes.
Have you experimented with the separation between the 2 microphones?
Yes. So this is the result of the 2 microphones.
Okay.
So that's as you can see here, the graph is not exactly from left to right, and one possible reason is that we use like 2 different phones to collect the audio information, and the recorded noise could be different, but we still be able to detect the time difference between the 2 signals, and the direction is correct for this situation.
Can you explain how you detected the red post thing?
Oh yeah, head post. Yeah. So that's some part we haven't finished. Finished yet. So basically, so this software, this part gives you the output of your angular acceleration, and even though I didn't move my head, there's still some angular acceleration output by this software, which means the RMU unit of essence have a large noise. And what we do in the future is we some filter to filter out the noise, and then do integration to get your head position. Yes.
So you have some generators listening around to the system?
Yes.
After
Yeah, so we are not using the tone generator all the time. So actually, when we record the file in the middle, we turn on the tone generator, and then we shut it off, and we just select the first frame to be our first frame detect the high energy at 1 kilohertz to be our first frame. But when we train our model, we actually just take the last few thousand samples to train our model.
Okay, I think we're done. Thanks.
Yeah, sure.
Yeah, we still have one.
Oh, we still have one more.
Oh.
Good.
Oh, okay.
Okay, yeah, there's a Y also. Okay.
Hi everybody. First, I'm sorry, but I guarantee we are the last group here, I believe. Our project is interaction between intelligent devices. Actually, we focus more on intelligent cars. I'm Yifan, and this is my partner, Zeyu. There's one thing I need to mention in the very early, because we used to have 3 people in this group, but we dropped these courses during this quarter, so it turns out to be a 2-people project. The deliverable goals this quarter is to realize the interaction between cars and interaction between car and the Bluetooth stations. And also we realize the interaction between human and cars. These are just the technical approach, which are the hardware and software we use. We talked this last demo session, so we just skipped this one. And the technique first is the interaction between 2 cars. Mainly what we did is to let the following cars to follow the front cars, but the following car doesn't have any sensors, so he knows nothing about the route, knows nothing about the speed, but just get command from the front cars. And I just want to show you a demo to see what we got. As you can see, there's only a bar as a following car. There's nothing else but just a chip.
100 account opens plus deposits with Weeble.
Wait, I don't think that is the sound from our.
No, I think there's too many windows.
Yeah, I'll close this one.
Don't close my windows.
Oh, I'm sorry, because I thought there was a sound bar, but it's okay.
Okay.
We can just go play that one. No, I mean the video we just showed is actually our one.
Okay.
Yeah. Not this one, but
oh,
yeah, it's okay. It's okay. This is our demo.
Okay.
Okay. As you can see, the following cars can follow the fronting cars, and that's mainly just about this. And how can I go back to?
Do a 3-finger swipe to the.
Okay. The next part is indoor positioning, which we use via RSSI, and I will hand over to Zeyu to talk about this part.
Okay. Good evening, everyone. RSSI means received signal strength indicator. Yeah. And the process is that we firstly use it's icon. It's just like a Bluetooth station, and we firstly it's the Bluetooth receiver, and it receives the signal from the icons, and also calculate get the RSSI value and calculate the distance between the icon, 3 distance. And at the same time, we know the position of the 3 positions, and based on the 3 positions, U1, P2, P3, and the 3 distance, U1, P2, P3, and we can calculate the position, coordinate position of this Bluetooth. And it's at the same time, the position of the car has been cut.
So here is just a live show of how the coordinates we build in our room when we test it. And the other part of it is just a value we got to get the coordinates in values.
Yes, we place 3 icons, and we assigned this one as 0, 0, and this normally we measure the distance between these 2, and it's 3 meters. So we assign it is 3, 3, 0, and it is 0, 3. And we use the
formula
to calculate the area of each triangle and divide the length, side length, and we get the height. And actually the height is the XY coordinates, the value here. The position in the coordinate. Now let's see the third demo.
Here is a demo that our car using that coordinate to go toward one of the Bluetooth station. It will just scan the RSSI value and make his direction prediction and go into that way to decrease the distance between the car and the Bluetooth station.
Now let's turn to the interaction system between multiple cars and group control. These are multiple cars and they communicate with a cloud. Each cloud is a kind of server. And each cars, they will record their position. The position is last process we get the position, right? And now the car will send the information, position information to the cloud, and at the same time it will send the destination that each one to go, and the cloud will the input of cloud is positioning and environmental information because some of cars have the sensors, and the output is pace planning. Just the cars while computing the optimized pace, and at the same time guarantee that these cars will not crash, crash each other, and then output the pace plan. Actually, the pace planning will change in real time because the position and the information will change real time. In this video, the server assignment that let the three cars firstly let the three cars get close to each other, and when the distance of each other is shorter than a value, they will go away from each other. So just two steps.
Okay, we talked about how the interaction happens between two cars and cars with one of the Bluetooth station or all three of the stations. So the final stage of our project is how we do the interaction between cars and human beings. We do use the Alexa to do the voice control. In the backend, there is a FlashAsk server running on the Raspberry Pi car. So the Raspberry car somehow became the central server of the whole system. We use NGRock on the Raspberry Pi to make it exposed to the public internet so that the Echo can do communication with our Raspberry Pi car. We build Alexa skills on the Amazon Developer Console, which will do the natural language processing on the cloud. And eventually, when we got the command from the Alexa API, we just use that command to operate in all three of our cars. Raspberry Pi to let master turn left.
Okay, master turn left.
Echo, ask Raspberry Pi to make slave turn right.
Okay, slave turn right.
Echo, ask Raspberry Pi to make slave go backward.
Okay, slave go backward.
Okay, I think that's good enough. And there is also a technique that will do the interaction between multiple cars and human beings. So you want to talk about this part too?
Okay. It's just a combination of two parts, and we have to see the voice control and the group control, and we combine these two together. The first step is same to the voice control, and the second part is we use two cards. Actually, use more cards, but in after demo we don't find two card situation, and the master car will control by voice, and the second slave car will be controlled by master car. Yeah. And because it's two cars, what we implement is just the following.
Echo, ask Raspberry Pi to let master go forward. So this demo is just an improved version of the first demo, which combine all three stages of our project. So it turns out to be the strengths and the weaknesses. First, one of the strengths is that we implement multiple interaction, not just human-computer interaction or computer-computer interaction. It's actually a multiple interaction system. And as to the accuracy, we combine the indoor positioning system with our sensor information sharing platform, which either of them work alone were not good enough to operate in both cars, but after we combine them together, the accuracy was increased. And as to the performance, since the natural language processing was using Alexa skills and was handled all on the cloud, only the car operation was be done on the edge, which means on the Raspberry Pi and through Bluetooth channel. So there's no latency problem. And the unification, we apply the same protocol and the Bluetooth language on multiple cars. So not only the Arduino car, but the Raspberry car share the same protocol to communication commands. As to the weaknesses, first, the voice control does not respond 100% correctly. I believe that is the way we're doing Alexa skills is not the best one. We are still improved on this part. Also, it seems that we need a better algorithm and maybe some better sensors to handle more complex situations when two cars or more cars are running at the same time. For example, during our test, when it comes to some very large degree turn, the sensor may just lose its target and the system go into a chaos sometimes. The last but not least, the RSSI value sometimes fluctuate, especially when the car is too close to the icon. I'm not sure if you noticed that, but in the icon demo, when the car was pretty close to the corner icons, it somehow lose its direction and not stop closely at the icon. So that's because when the car was too close to one of the icons, the RSS value is not that reliable. We done topic research before, and there's not many previous works on how cars and cars interaction between each other, but we do use all these. Some are code, some are just algorithms, some are just a platform to realize the whole project. And here is just a contribution of what I do and what you want to do. Any questions at this point? Yeah.
So when there were like one part on the other, I noticed that when it moved, it would readjust if it got off course. How would it do that?
It's actually a result of both the indoor positioning system and the sensor sharing system. So we rely on both the information from these two platforms and to adjust the position of the cars. So when we are doing follow, we need to make sure the following cars and the leading car somehow in some sort of line so that they can work very smoothly.
Did it work with like longer distances?
As long as we apply the icons to make like an electrical fence to build that coordinate, it can work in that long distance. But if like a very, very long distance, like outside door, the Bluetooth icon is not available to work in that long. So we may need to apply like GPS or
because
something.
the Bluetooth, the signal distance is limited.
So, did you intend the methods you are exploring primarily for these kind of small scale, whatever, toy cars, toy scenarios? Or is it more like a proxy for technologies which you think would be there in real cars? Cars? Because I guess the reason I ask is some of the things that you are doing are probably not going to make sense with the cars, and some might. So what was your objective? I mean, do you see, like, if you want to go forward in this thing, is the goal to make cool multi-car toy environments? Is that the market, or is it that these are technologies that you see for actual autonomous vehicles?
Well, personally, I would like to see what we have done is kind of like the simulations that we want to see to be some market technologies. Like something like we use ultrasonic sensor, but in actual, like what Tesla do is much more better
It's
sensor.
like radar.
Yeah, and we use icons for indoor positioning, but for the outside, for the real car, we may use GPS, which provide a better result.
So that in that case, what what aspect of your project will, what methods will translate as they are to?
I would like to say to the algorithm, because we make the following algorithm. Although we are basing on those like cheap sensors, but it can be replaced by the better sensors, and it still works as long as we can test it on real cars.
Yeah, I think what we try is to make a sensing information sharing system and try to realize a centralized control.
And the command system between two cars without pilot.
Yeah, just like Brain, or Google Brain, where it will control. In the future, maybe we'll Brain, just like a server will control a lot of cars and a lot of self-driving cars. Just a try, but we only use 3 to 4 cars, and it can be moved forward. I think.
Yeah. Okay. Anyone with any more questions?
Okay,
great.
Thank
I think
you.
we're already on the time. So thanks everyone. I think the projects were all great, and what I'll do is so firstly make sure to return all the material. So my plan right now is I'm going to be in my office on Friday, so that would be a great time. I'm going to send out a time window. But if that doesn't work for any of you, if you want to return it earlier, then go to my lab and return to your mentor or one of the students. But then have them send an email and CC you what are all the items returned. You can also return to Swapnil or Yo-Yo, who are my students in the class, so they can accept the thing. But otherwise, Friday you can Friday afternoon I'll just have some time slots. And the other thing is that the project URLs. So basically, all your material should be in your GitHub repo. Okay, so it basically means your website is a branch in the GitHub repo, and all your code and all should be just organized by folders, basically be there. And make sure that the repos are either shared with me. I had sent out my ID long ago. I think it's M. Srivastava or MB Srivastava, one of the two. But if not, if you don't mind, just make it public. Okay, that's probably the cleanest thing to do. Okay. So and otherwise, what I'll do is, in case you just want to make the videos of your presentation here as the one which you want to just include, then I'm going to just put the whole thing in YouTube, and you can extract your portion out of that. So.
On that part, so do you have a preference? You know, like say like we have a short demo or something to add. Is it okay if we?
Yeah, you should just add it. So you can just use whatever QuickTime or something to just append whatever you want. Yeah.
And like that's generally fine. So
yeah,
just recording is fine.
Yeah, exactly. Yeah, right. Yeah, I mean, probably don't want to redo your oral presentation needlessly. So yeah, okay, great. See you guys.